Yeah, when we run a laptop, like deep hours, yes, it might be one of those watts, but it's still, I think it should be a whole card. But not my guess, because that would be USB-C power.
Good morning, everyone. And welcome to the second day of SYCO 13 here at UVM. I'm delighted to introduce our invited speaker for today, Martin Carbonen, who completed his Master of Science in Mathematics and the Foundations of Computer Science at the University of Oxford, and his PhD at the University of Edinburgh. He had a postdoctoral fellowship at the University of Ottawa and currently a postdoctoral at UCL. This talk today is titled "What's Going On with Categorical Composable Cryptography." Let's thanks.
Thanks for inviting me, and thanks for coming for the early morning session. If I wasn't speaking, I'm not sure I would have made it myself. Anyway, so the talk is made out of 3 parts. The first one is sort of a recap of work I've already done with Anne Broadbent. And then there's 2 further parts on sort of work in progress with other collaborators. I'll name everyone in due course. As a caveat, the first part is something you might have seen if you've seen me talk about this topic before. And I'll also warn that that will actually be the bulk of the talk for 2 reasons. The first reason is that, I mean, these other things are work in progress. And while we do have more results than I'll present to you today, I'd like to let the results develop a bit more so that, I'd have a better sort of story and picture, full picture understanding of what's going on there, instead of just piecemeal results like today. And the other reason is that, well, it's much easier to reuse old slides than to make new ones. Anyway, so now let's get started. So the first part is based on joint work I did with Anne Broadbent while I was at Ottawa. And the starting point is really this fact that's very well known to cryptographers, but surprised me a lot when I learned about this, namely that security in cryptography is not in general or sort of by default composable. Meaning that while cryptographers have all kinds of nice protocols, wonderful protocols for all kinds of things that are all provably secure in some sense of the word, but now if you take a bunch of sort of secure protocols and put them together, the end result is not automatically guaranteed to be secure. It in general needs a further security analysis or a proof, and it could even fail. You can even find protocols that are, well, secure sort of in isolation, but if you're running 2 copies of it in parallel, that could very well fail to be secure. Actually, ELO ratings in chess give a nice illustration of this. In the interest of time, I'll just leave it at that puzzling remark. But I mean, if you want to learn more, you can ask me later, whether in the questions part or later on today. Anyway, cryptographers know this problem exists very well, and they do have various approaches to dealing with this, so various frameworks for composable security. I think it's fair to say that whatever their merits are, the mainstream cryptographers aren't, most of cryptography isn't usually done using these frameworks. And I think there's 2 reasons for it. One is that this composable security is genuinely a higher bar, and it could even be impossible to achieve for some tasks that we still want to use in cryptography. So then you just work with the kind of security, weaker security that you can actually achieve. But the other reason is that these frameworks are somewhat difficult to work with. So then that's also somewhat limiting the amount of composable cryptography that's being done. And now in our viewpoint, we think of cryptography as sort of a resource theory as is understood in categorical terms. So then we'd have various resources, which would basically be the objects of our category. And these would be some sort of shared resources between parties that achieve some cryptographic functionality. So you might have a shared key between 2 parties, or you might have a channel that is secure or fails to be secure or whatever, and then you try to take some of your starting resources and then build a new resource out of them, and then that designing such a protocol that is secure is sort of the basic task of cryptography. And then mathematically, we'll sort of, I like to think that the sort of resource theories sort of come from taking some kind of Grothendieck construction, and then the sort of secure transformations between resources then will be a sort of subcategory of the resulting category of elements. And an example we'll get to later in this first part is the famous one-time pad, which we now think of as something that takes a shared key and an insecure channel and then promotes it to a secure channel. And then the nice, curious fact about this is that actually this boils down to something that people working in certain kind of category stuff would know well. So it boils down to axioms of a Hopf algebra together with something called an integral, which is basically the uniformly random secure key that's used here. Yeah. I will discuss this later. Yeah. But roughly correctness is that if everyone follows the protocol, then we actually achieve the target channel in question. So we successfully send messages from Alice to Bob. And then security is captured by saying that, well, whatever the evil parties may do, well, they can do nothing worse than they could do if we had the actual ideal resource that we want to emulate. And now, if you're one of those people who just wants a sort of short overview, then this is enough for part one. You can go nap now and wake up when part two starts. But the rest of you, I'll show some more details. So the way cryptographers usually sort of capture this composable security is that they usually have all of these frameworks have this thing at their heart. And depending on who you ask, they might call it the real world, ideal world paradigm, or sometimes they'd call it the simulation paradigm. So roughly the definition is something like this. So you have some protocol P, and you want to achieve some ideal function of the F from some resource R. And then the way you capture the security on it is by saying that, well, anything the attacker could do in the real case, when you're actually running the protocol together with your actual resources, well, there's some other thing the attackers could do, which is often called a simulator, such that the end results are, well, either equal or at least they're sort of close enough or computationally indistinguishable. So in other words, anything the attackers could achieve in the actual case when we run the protocol, they could also achieve it in the ideal case. And now if our ideal resource is sort of secure by design, then that implies that our actual protocol is at least as secure as the ideal thing, which sounds like a good enough a standard for security. But then they want to make this precise, and roughly there's sort of, you could split the existing frameworks into two kinds of approaches. So you either pick some very detailed model of interactive computation, and then do instantiate all these definitions in that kind of framework. So universal composability would be maybe the most famous framework for this, for classical cryptography. And then there's something called abstract cryptography, or depending on who you ask, it's sort of related or the same thing, something called constructive cryptography. And I think these are, their heart is in the right place. They sort of want to do things more abstractly without tying themselves to a particular computational model. And now I guess this is the kind of audience where I might get away with saying this kind of things. So I think their main issue really is that they didn't know category theory and then felt the need to invent something not quite as beautiful in its stead. But now today we'll sort of fix that here. So the main result of this work, in a sense, is that you can capture this kind of simulation-based security in an arbitrary, well, symmetric monodal category and some further structure on it. And then the result is that these secure protocols give you a symmetric monodal category, meaning that they can be composed sequentially and in parallel. And now this is the kind of audience where I probably don't need to sell you too hard that category theory comes with some benefits. But anyway, it's kind of nice that we're not tied to a particular computational model. In principle, at least, we could model all kinds of different things, whether it's classical computation or quantum, whether it's synchronous or asynchronous and so forth. Of course, what things will be secure will depend on the model you choose, but the very fact that doing sort of security composably gives you sort of a symmetric monodal category won't depend on the computational model. Another thing is that we have these abstract attack models, so hopefully we'll be able to instantiate with many different kinds of, like have a kind of a fine-grained way of modeling different kinds of attackers, not just sort of malicious attackers that might do arbitrary things, but then have like more limited kinds of attackers. Maybe there's a bunch of them, maybe they cooperate, maybe they don't, and so forth. Now, in the first part, I'll mostly talk about sort of perfect security, but I'll mention already that we could do also security in the more usual case where it's up to computational indistinguishability, or perhaps even security up to some explicit epsilon, or 0.1 or 0.001 or whatever. And finally, because we're using category theory, we get to use string diagrams, and we might be able to connect to other fields of theoretical CS and maths where category theory is commonly used, and maybe use that to bring ideas back and forth between cryptography and these other fields. So now, I mean, we've seen lots of these string diagrams in the talks up to this point. So maybe this slide is mostly useful to set up my convention, which is that I use the so-called optimistic convention where pictures go from bottom to top, as opposed to the pessimistic convention where everything goes down to hell. I'm open to changing this with my co-authors in some of the future works to going from left to right. I've even seen some talks where someone had lots of dual objects, so all morphisms had a arrow. All wires had sort of an arrow, but then they had set their things so that the arrows were always pointing from left to right, but you were supposed to read the pictures from right to left. Anyway, we're today not in that case, we're going from bottom to top. The other thing I'd like to recap is these resource theories. They sort of come up in physics, but I mean, for me, I like to think of them as basically just particular kinds of symmetric monodal categories where we sort of often ask very different kinds of questions. So instead of asking like, oh, does this category have limits or co-limits, or does the tensor product preserve co-limits, or how does it relate to other symmetric monodal categories or whatever? But the main task to solve is really, is there a morphism between these two home sets or not? And that should be in general difficult in some of these. But informally, they're used to capture the kind of setting where you have resources and try to transform them. So informally, there's something like a resource theory of information theory, which studies questions like this. So you have a bunch of channels that might be noisy. So you send a message, but something else comes out. And then you'd want to find some protocol, some encoding that sort of gets rid of the noise, or at least improves the situation, so you can simulate having a channel with better noise properties. And lots of these come up in quantum mechanics. So for example, this question is really captures the resource theory of entanglement. So we have a bunch of parties. Usually people study just a case of two parties, but there's some work on more. So you'd have a bunch of parties that share some quantum state between them, but they're only allowed to do local quantum operations on the system. And then between each other, they can only do classical communication. So that's the LOCC, local operations and classical communication. And then the task they want to solve is, can we transform this quantum state to that one? And if you can, then you'd say that, well, the starting resource was at least as entangled as what you get at the outset. You could think of any preordered commutative monoid as capturing this kind of situation as well. So then the elements of the monoid would be some kind of resources. And then, well, you have the monoid operation, which corresponds to putting resources together. And then the preorder sort of captures how resourceful something is. And conversely, if you sort of had a symmetric monodal category, and if you first took a preorder collapse and then identified isomorphic things, so sort of basically, well, then you could force it to be commutative. Well, I guess it would be partially ordered at that point and not pre-ordered. But anyway, you can get structures like this by sort of forgetting a lot of the structure and just remembering whether there is a protocol or not. And now these are studied in detail in this nice paper by Bob, Tobias, and Rob. And in their formalism, the starting point is that you have some kind of large symmetric monodic category C of sort of all processes. And inside of it, you have a subcategory of free processes. And now when I say free, I don't mean free versus forgetful or anything formal like that. It's more like the subcategory specifying what processes you consider as free for the resourcing question, as opposed to sort of costly processes. So for example, these would be roughly the LOCC operations, and then C would have all quantum operations that the parties could do together. And now one of the constructions they do is this so-called resource theory of states. And you could define it as follows. So the resources are given by states in C, so maps out of the tensor unit. And then what's a conversion from one state to another? Well, it's given by a morphism in this subcategory, so it has to be a free conversion that transforms the starting state to the target one. And now the sort of first observation we can do here that lets us generalize this situation is that you can actually realize this as taking the category of elements. So you first include the free categories in C, then you home into set. And if you then take the category of elements, you get exactly that resource theory out. So more generally, if we had a functor to set, well, this works also for pseudo functors in the cat, but that's not needed today. So you can build a new category. So the category of elements, where your objects are pairs of something in the starting category, and then an element R in the domain in the set F of A. So I'd like to think of it as sort of like you have a resource R of type A. And then morphisms of this form are given by conversions. So a morphism from the type of R to the type of V that not only goes between the correct types, but it actually converts our starting resource to the target one. And then it's a nice fact that as long as we started off from a nice functor, then this automatically has a symmetric monodal structure. So we don't need to sort of construct it by hand or check by hand that we have a symmetric monodal category. So now let's do a variant of this, where instead of, we're still sort of homing out of the tensor units, but now before that we take n copies of C and tensor them together, and then include n copies of the free subcategory. And then if you compute what the end result is, well, objects are now given by a list of objects of CF, or equally of C. They have the same objects after all. And then a morphism on that goes from the tensor unit, but to a tensor product of all these objects. So you could think of that as saying that, oh, we have a resource is given by specifying for each, we have n parties here. And then a resource of a given type is given by saying that, oh, we have n parties, each of them has their sort of port corresponds to a type of AI. And then we have a resource that goes to is of the tensor product type. And then what's a resource conversion? It amounts to each party choosing what to do with their part of the system so that they collectively succeed in transforming R to S. So we could think of this as sort of a nice collaborative setting where these n parties together try to figure out, is there a way we all together can transform R to S? Let me actually mention an example here. I should have done that already for the previous one. So if C was finite sets and stochastic maps, well, inside of it, you could take the deterministic maps. Well, now in the one party setting, then your resources are stochastic maps from one element set to your set A. In other words, probability distributions on set A. And then your resource conversions would be deterministic maps that transform your starting probability distribution to the target one. And now in this n-partat setting, now we have sort of our n-partat joint distribution. And then we want each of the parties to just act deterministically and locally on their part of the joint distribution so as to collectively transform the starting joint distribution to the target one. But now, in this case, there's no security. All the parties trust each other, they collaborate. And now to get something a bit more cryptographic going on, we could ask, well, what if some subset of the parties is evil and they might do something else? So assume that the first K parties are honest, so they always follow what the protocol does, and then the remaining ones do something else instead. And now if we want to model this sort of security body simulation paradigm, we'd say that our conversion of resources is secure if whatever the parties A can achieve in the presence of the protocol, they can also achieve in the presence of the IDO or the target resource. Well, each of them has access to their part of their resource, right? So together we have, I mean, we always start from the resource R, and now this is just notation for the tensor product of the, so the first K parties restrict to their part, right? So F1 to Fk, yeah.
That was the,
If
you are honest, you know that how many parties is and you know that how many parties resources.
Yeah. So in this setting, where assuming that there's a fixed number of parties, it's known for everyone when we design protocols. It's a separate question to then go to settings where the number of parties is not known in advance or might change during the protocol or something like this. For now, we're ignoring that kind of complication.
So just that both honest and dishonest parties know how many parties.
Yeah. Sure. Yeah. In this setting. And this is already enough to model some basic things in cryptography. So for example, the standard problem of like one-time pad, you could think that there's three parties, Alice, Bob, and Eve. So Alice and Bob want to talk to each other, and then Eve is some external eavesdropper. But of course, then if you're modeling some kind of more complicated thing, like, I don't know, some blockchain cryptocurrency kind of thing, then you might have a setting where the number of parties could change, like new people can join in or leave or whatever, and then that's a whole different ballgame. But for now, in this sort of toy setting, the number of parties is fixed and known to everyone. But anyway, so then the correctness would be the equation from the previous slide. And now we could capture security by saying that, well, for any A that the attackers could do on their part of the system, there exists a B such that the end results are the same. And actually, a nice thing is that in this case, it's enough to prove that this equation holds just in the case when you leave open the wire of the evil parties, in a sense that sort of the interface that exposes just, well, whatever the evil or malicious parties could do. And you can check that for that one, there should be some corresponding thing B that they can do. Because then, well, whatever they plug A here, you can just plug the corresponding A here and the equation remains true. So now let's see how we sort of model this kind of thing in the abstract. So if we think of all resource theories come from these Grothendieck constructions, then that's really capturing just the correct ones. And then we want to model security somehow. Well, I'll add further structure that specifies for each sort of protocol what the malicious parties could do instead. So in the previous setting, it would be saying that, well, if your protocol says that you're doing F1 to Fn, then you can freely change what the malicious parties do instead. And then we'd capture security by saying that, well, whatever, for any attack on the protocol, there's an attack on the target such that the end results are equal. And roughly, I could sort of formalize it as follows. So I'd say that we have for any F, there's a collection of morphisms, A of F. And now when I write a composition for sets, I mean, well, take all the composites that are well-defined. So now the first action would say that, well, the attacks on the sequential composites are sequential composites of attacks or sequential composite and vice versa. So I'm saying an equality of sets. So then the inclusion from here to here says that if take any sequential composition of attacks, then that's an attack on the sequential composite. And now for tensor product, one might be tempted to say a similar thing, but that would be way too strong and sort of make it too easy to get a sort of security for parallel composition. So the whole point of why parallel composition is sort of difficult for security is that you don't need to attack the two protocols running in parallel just on their own right. You can sort of play them off against each other in complicated, interesting ways. And the way we capture that is by saying that, well, you could sort of any attack on a tensor product, you can factor it as an attack on each of the parts on their own and a step that sort of plays them off together somehow. And conversely, if you do anything of this sort, that will be an attack on the tensor product. Now, I'd be happy if I had a more categorical description, like this almost looks like a functor, but there's some further constraints that I don't want to go into now. But also there's this part that sort of doesn't quite make it into a functor. And moreover, there's this further caveat that I can't assume that the set of attacks sort of respects our type system. And that's actually kind of important because our protocol could say, for example, that some parties are supposed to delete some information, map into the sort of unit type or something like this. But of course, the attackers might not care about what we ask them to do, and they might sort of try to extract the information, map somewhere else. So we can't sort of remove that there. Anyway, even if this is sort of slightly ugly from the categorical point of view, it does work in that we do get composability results. But let me say a bit more why these axioms might be plausible. So in the case of like, oh, we have k parties and some are malicious, we can just do this factorization pretty easily. So in the first one, well, if you just take our attack A on sort of the composite, you could think of it as, well, first there's the identity here, which is just an attack on F, and then you're doing an A, which is then an attack on G. And now if you're doing an arbitrary attack on a tensor product of two resources, and attack A, you can think of it as first you're doing the identities here, which are the attacks on R and T respectively. So this part, and then you're sort of doing the actual really meaty part that plays the two protocols against each other. And you could think of that as the attack on the identity protocol on the tensor product of these two resources. And now in this kind of setting, one can then prove that indeed we have this composition theorem. So we already know that we have because we're taking a sort of monodal Grothendieck construction, that we have a symmetric monodal category of all correct resource conversions. And now we're defining restricting a subcategory. So to show that that's an SMC, it's enough to check that the coherence isomorphisms are there, and then it's closed under these operations. And I won't show the full proof or in that sort of abstract proof, but it's sort of easy to do in this particular case we've had here. So if you imagine that, well, again, it's enough to show that things work for the initial attack where the adversaries just leave open their interface. Well, now, because F is secure, there has to exist some A such that this first equation holds. Or I guess, if you remove the G parts, that's what we get. And now because G is secure, then we know that there's some B that replaces the identity. I mean, you could think of the identity here as an attack on G. So we get this. And similarly for the tensor product, oh yeah, okay, go ahead.
Similar in some spirits to the Bayesian version?
That's a good question. I haven't thought of that yet. Yeah, maybe let's discuss that in detail later. But I mean, informally, what these do, sort of what I mean, these are often sort of the reason they call them simulators is that they sort of simulate what the evil party would see, sort of the information they would get in the honest case. So it's a bit like in the one-time pad, as we'll see later, we see that the malicious part, the eavesdropper, basically just gets uniform randomness. So then this A here is just a simulator sort of throwing a coin on their own right. Anyway, that's the intuition to have for this kind of thing. Or more generally, if you see they see multi-round communication between the parties, but they can't really understand what's going on, they sort of just fake communication between the honest parties, and that's sort of what these A's are doing. Anyway, that's the intuition I'll give now. I'll leave it to you whether it's similar or not. And now, in the case of parallel composition, it's similar. So if we just think of, oh, there's two. I mean, it's easy if we just restrict to the identity attack. So the wires that open, and then, well, R is secure. Sorry, F is secure. So we get this A here and B is secure. And now we've shown that, oh, well, in the worst case or the relevant case here where we leave the attacker's interface open, there's a corresponding simulator or attack they could do such that the end results are the same. And now I worked in the simple case where it's already always known that, oh, it's these parties that are dishonest. But now it's easy corollary of this that, oh, if you consider multiple kinds of attack models at the same time, then and want to be secure against each of them, that's automatically secure as well. And now this gives some kind of a abstract toy model for what the situation people consider in multi-party computation. So you'd have your n parties, and then you could say that, oh, I want my protocol to be secure against any malicious subset, provided that malicious subset is not too large. So let's say it contains at most half of the parties or at most 1/3 or something like this. Now we'll start building towards the one-time pad. So we don't really have to restrict ourselves to just resources being states. We could build our resource theory where our resources are given by morphisms, and then our resource conversions are given by sort of these columns that transform columns made out of three maps that then try to transform a starting resource to a target one. And I guess you could, more generally, you'd have a list of morphisms F1 to Fn, and then you could have a column that sort of uses them in an arbitrary order that you sort of choose as part of the specification of the protocol. And similarly, you could do an n-partat version, where then each morphism comes with, chosen decomposition into n parties. So each shared resources are now a morphism, where each of the n parties gets its own input interface and output interface. And now to model the one-time pad, we'll do it in the three-partat case. And actually, in this case, for now, we could even fix our C to be the category fin stock, so finite sets and stochastic maps. This is way too limited for more interesting cryptography, but for now, for this one-time pad, we can live there. So now our resource would look like this. So there's three parties. Each of them gets to put their own input into the function and gets one input out. And then for notation convention, I'll actually omit the labeling the sets. And we have three parties that I'll just call Eve, Alice, and Bob, and then label each of the wires with just the person owning that wire. So I'll write something like this. So I have a copy map, and I'll just write this to me that, oh, Alice owns the input one, and Eve gets one half, and Bob gets the other half, instead of something like more complicated like this, where I keep track of the type of this copy map being M for the message space, or I guess even more formally by listing everyone's inputs, because formally, I guess everyone gets an input and output. So you can model this by saying that, well, some of the parties have a trivial input or a trivial output. So anyway, that results in simpler notation. And then we can discuss what the situation is for one-time pad. So we have this channel from Alice to Bob. However, it has the drawback that anything Alice sends, it gets leaked to Eve. Now one could do a more complicated version where the message goes to Eve, who might then tamper with it and then send it to Bob. That's a different question. So I guess we still have a channel with some security guarantees, namely that Eve can't change the message there. But anyway, it still leaks information to Eve. The other resource that they need is this shared random key. So we have a uniformly random distribution here, and then that gets copied to Alice and Bob. And importantly, Eve doesn't get a part of this key. And then what they want to achieve is a channel that just goes from Alice to Bob. And now, in addition to these resources, everyone can do sort of computations locally on their part of the system. So let's see what kind of computation they need. So we'll need a group structure on this message space. So usually this is, messages are just bit strings of some fixed length n for this. And then this would be pointwise XOR. And now we can capture the multiplication in these usual terms that we have a monoid. We also need the fact that copying and deleting form a comonoid. And then the fact that we have a group can be captured by saying that we have a bi-algebra, so this equation here. And then the fact that we also need to say that we have inverses, and that's captured by this equation here. So if you take our input, copy it, and invert one of the copies and multiply together, well, you can, it doesn't matter what you send in, you might as well delete it. You will always get the neutral element of the group out. Now, this inverse thing is usually invisible for the one-time pad, because if you're just working with bit strings mod 2, then taking the inverse is just the identity map, so it sort of disappears from the pictures. But anyway, it works like this. And now we have this key, and the fact that it's uniformly random can be captured by this equation, saying that, well, if you sort of have a channel and add random noise to it, uniformly random noise to it, it completely destroys the message. So you might as well just delete the message, and what comes out is uniform randomness. And now we can draw the protocol. So the protocol, maybe it would be useful to further dash lines here. So this is the shared starting resource, the key. This is the leaky channel from Alice to Eve and Bob. And now this part is sort of Alice's part of the protocol. And then this part on the right is Bob's part of the protocol. And we also specify a part for Eve. So everyone gets told what they should be doing. However, we want this to be secure. So it's not enough that, if you do computations here, you can show that this actually results just in a channel from Alice to Bob. But we also want to have some guarantees what happens if Eve disobeys the protocol. Now we could consider a situation where Eve instead listens, and actually this is sufficient, because anything Eve could learn from the ciphertext or from hearing the encrypted message, they could learn by doing some computation on it. So it's enough to it's enough to reason about this case. And now we can use the axioms I've shown you one by one to compute. So the first one, we use the bi-algebra equation here. Then we associate and co-associate, I guess, the multiplication and co-multiplication respectively. Now we have a thing with its inverse added together. Then we have units and co-units going on. And now we have the fact that the key is uniformly random. And then again, we have a co-unit equation. And now if you take all this together, we're showing that, whatever Eve gets here, if they disobey the protocol, is equal to actually just Alice and Bob having the IO resource, the channel they want to build, and Eve just producing randomness on their own right. And now this picture here, you can think of Alice and Bob just have the channel they wanted to build, and Eve is trying to attack it by just producing, like flipping a coin on their own system. And now this sort of shows security in the sense I defined it earlier. So in more concrete terms, anything Eve might learn from the ciphertext, she could compute without having access to the ciphertext just by flipping a coin. Now, the problem with one-time pad, of course, is that you need a key that's as long as the message. And getting those keys shared is complicated. And in particular, you can show that it's not safe to reuse keys. That, if you just copy the output of a uniformly random thing, that's not two independent uniformly random things. So now what they could do instead is to take something called a computational secure pseudorandom number generator, which would require passing to a different category to model that kind of thing. But informally, for now, they could have a thing that basically it's a deterministic map, which guarantees that if Alice and Bob run it on their copies of the key, they still have the same key. But this would have the further property that if you run it on a uniformly random input, the output still looks uniformly random, even though it's in a larger space. And then if they had such a thing, they could sort of expand a short key to a long key. And now we could then compose these two protocols together. And now it would automatically be secure because, well, it's a composite of two secure things in this framework, and we have the composition here. Now, I mentioned earlier that we worked in the perfectly secure setting. The other aspect that sort of was a limitation here was that there's no sort of communication between the parties. Everything happens via the functionality that they sort of share. And now in some situations, we might want to change both of these assumptions. So the second problem that all the communication happens via shared resources that have to be explicitly given. That's something people usually don't want to have to do when they study multi-party communication. So in multi-party secure communication, people would usually assume that the problem of pairwise secret communication is already solved somehow. But you still want to solve, like, oh, how do we collectively securely vote? And that's still, even then, that's non-trivial, even if you can communicate securely pairwise, for example. So then to model that kind of thing, you could just replace this, change this resource theory by saying that some resources, you just stipulate them to be free, and then say that, oh, a general protocol from R to S is actually a secure protocol from R times something you stipulate to be free to S. And now X could contain the kinds of communication channels you want to consider to be free in this case. The other issue is that I had perfect security, so everything was an equation. Well, that we can replace. So in abstract terms, you could, instead working with an equation, you just work with an equivalence relation that respects the structure suitably. And then informally, that would model computational indistinguishability. Or we can actually even instantiate this setting with a category where we do have an interesting non-trivial equivalence relation that actually is the usual notion of computational indistinguishability. Or we could work with pseudometric and then work with a sort of sequences of transformations that are sort of secure in the limit. Or maybe you want to work with just security up to some fixed epsilon. And both of these we sort of developed the theory for in the paper. For example, for this pinstock thing, we can then pass to efficient sequences of stochastic maps and then do things there up to computational indistinguishability. And we can model, for example, the Diffie-Hellman key exchange, which solves the problem of, well, how do you get the keys in the first place? By only communicating in a way that the eavesdropper can hear. I'll mention just some other results we have in that paper. So we also, I mentioned earlier that this composable security is a strong constraint. And actually there are some known limits on that. And we do abstract versions of these. So if you have 2 parties or 3 parties, and instead of, oh, one of them is evil, you say that any single one of them could be evil. So Alice wants to have a guarantee against Bob, and Bob wants a guarantee against Alice in the 2-party setting, or in the 3-party setting, you want a guarantee against any single one being dishonest. Then there's some limit on what you can do. And we do have abstract versions of these. And then finally, there's some nice results that might be useful later in the upcoming work that show that under some assumptions, sort of strong model functors between categories preserve security. So you could think of, for example, embedding classical computations into quantum computations. And well, you can say fairly trivial things using these, but for example, if your thing was perfectly secure, then it remains perfectly secure in the quantum setting. But now if it was computationally secure, well, then it's not so clear because the quantum adversaries might have a different notion of what's computationally efficient. But if you had a classical protocol that's secure for whatever classical computations capture efficient quantum computations, then it still remains secure if we had actual quantum things instead. And now let's move on to these upcoming works. So this is joint work with quite a bunch of people. So Puya, Andre, Markov, and Phil. And now our goal is to capture formally a lot of these other frameworks to composability. So for example, universal composability or abstract cryptography, and then use this kind of lifting result I mentioned earlier to, for example, prove that, oh, if you've already proven something secure in this framework, it's automatically secure in this other one, or tools or ideas and so forth. And now I'll sketch briefly how we model universal composability in this kind of setting. So roughly they work with interactive Turing machines, and each of them has some identity, which you could think of as a string that just tells the name of the machine. And they also have a communication set that tells which machines this particular machine in question communicates with. So who it expects inputs from and who it will send queries to. And now if you have a set of these, each of them with their own name, and now you have some further identity S. Well, now if S is the identity of a machine in our set P, and it expects input from some machine outside of it, then we'd call S an external subroutine identity. So S is sort of an open part of P. We're expecting something to come in, and S is sort of a subroutine of that outer part. And conversely, if S is to receive output from some machine P, then S is an external main identity. Okay. So now an open protocol is roughly a finite set of these interactive Turing machines like this, up to renaming the internal identities. So those are just machines that are invisible outside the protocol. Those consist of machines that talk between each other inside the protocol. And now we will build a category where roughly speaking, a morphism from two finite sets of names of machines. It consists of a protocol whose the sort of external subroutine identities are inside S, and then the external main identities are in T. And the way this category, roughly speaking, works is that, well, if you have two such things, you can just take the union of these two sets of Turing machines. You might need to rename the internal identities to avoid names clashing, but that's fine. And then the disjoint union of sets will give you a monoidal structure. So in this way, we'll get a symmetric monoidal structure in which we can sort of instantiate this theory. There's some further things that we'll need to do for this. So to model really like a variant of how the adversary behaves is that, well, we actually pass to a certain class C category. I think I'll leave more details out there. We might also want to do an n-party version where you have sort of n parties, each of them consisting of their own set of machines. So a single party might sort of have access to multiple machines, but then these different parts don't get to communicate. They only get to communicate within a single party. And then you might have further parts. So you might restrict your machines not to be arbitrary, efficient, interactive Turing machines, but you might want to have some rules saying that, oh, if the adversary corrupts you and comes and asks you a question, you will just hand over everything you have, for example, or something like this. So this is roughly a sketch how we'd model universal composability. And there's lots of things to iron out if we really want to capture UC as it is done. So I think even this is for something called simple UC. And then in the full-blown version of UC, they have this ability that machines can spawn further machines during the protocol execution. That gets quite hairy to model in categorical terms. And now there's this other collaboration with two people here, so Robin and Fabio, and also Mike at Oregon State. And in this collaboration, our point is that, well, I said, okay, usual cryptography is not composably secure. So often that would be, instead of simulation-based security, they call it game-based. So we have some kind of security game that captures some aspect of security, but doesn't guarantee necessarily that security is preserved on the composition. But those things are still somehow have a categorical, potentially a categorical flavor, because those are still saying that, oh, two sort of games or somehow settings are indistinguishable, which roughly you could think of asserting some kind of equation or an equivalence relation between two things. And maybe this is something we can model using string diagrams. And we have sort of a small body of results in this framework. So Mike has a very nice book on cryptography called The Joy of Cryptography. And a lot of the protocols there seem to be amenable to this kind of equational or pictorial reasoning. And I'll mention just one. now, so we need some further generators. So for now, I mean, we have other ways of thinking of this, but for now, let's think of this new box that's now a stateful map. So it keeps track of everything that's been sent to it. And it checks that any input given to it is new. If it's seen already the input, it just aborts, it crashes, the whole protocol crashes. But if it's generally a new input, it just passes it through as is. And you could also have it for pairs or whatever n tuples. So then it checks that the pair itself is new rather than each element of the pair. And now there's two equations I want to assert. Well, this one should be easier. So if you're sending something and checking it's generally new, it's enough, and then copying it, it's enough to check if this holds for either one of the copies. And the other property is more surprising, perhaps. So if we think of this as uniform randomness, but really as a sequence of uniform randomness, so you get to choose n, and then you get n bits of randomness. Then as a function of n, it turns out that, well, not really an equation, but up to indistinguishability, it doesn't matter whether we sample or whether we sample without replacement, because as n gets large enough, you're very unlikely to get clashes. And then the other thing we need is a pseudo-random function, which is basically a deterministic function that behaves as if it was selected uniformly at random from the set of all functions. And then the relevant equation for it is that, well, if it's chosen uniformly at random, is that, well, if you give it a new input, then it really looks like, well, you can just ignore the input and choose something uniformly at random. And then a pseudo-random permutation is just the same thing, except it should have an inverse, so be invertible, a permutation. So now this protocol called 3-round Feistel achieves the following thing. So if F1, F2, and F3 are pseudo-random functions, or you could think of just as a single pseudo-random function, but each gets their own random key that's sort of private to F1 to F3. There's also analysis for this where they have a shared key, but that's more complicated, so I'll ignore it for now. Then we can do this kind of thing where, I mean, we take two copies, we're getting pairs of things in. We suitably copy things and add things together. And now the claim is that this thing is still a pseudo-random function, but moreover that it's invertible. I'll leave it out for now, the proof, but I'll claim that it has an inverse given by this. And you could just do a computation and use the fact that, well, I guess implicitly here I'm using computation over bit strings, so the inverses are given by the identity map. Otherwise, you need to add inverses in suitable places. But basically, the f's will cancel against each other, and that's why you'll get the fact that this inverts the first one. And then the other thing to compute is that it's a pseudo-random function. So if we give it generally new inputs, then the outputs look as if they're independent and randomly sampled. And then we can use some equations. And the first one is actually really where the meat of the proof goes. And I won't discuss that now, but we do have some kind of a computational understanding of that as well. And yeah. So sure. So this is still a multiplication of some Hopf algebra, but you could just really think that it's just a pointwise XORing of bit strings. And then we have copying and deleting, and we still assume the sort of Hopf algebra equations. And now the first part is a lemma saying that, well, when if the inputs are suitably random, are unique, the input pairs are unique, then whatever is coming out of here is always new as well. And that's requires its own proof. I'll ignore it for now. And then we can use this equation we had before. So I'm just sliding this uniqueness check past the copy. Then I'm using the fact that F2 is a pseudo-random function. Then I use the fact that, well, if you add uniformly random things to a channel, you might as well delete the input. Then I use the birthday bound, which goes into proving that, well, you can replace something with replacement with something without replacement. Then we again would slide the uniqueness check to F3, and then use the fact that F3 is a pseudo-random function. And then again, this is uniformly random, so we'll get a deletion here. And then if you chase all of it through, you'll get the fact, oh, we passed through this uniqueness check and just delete it after, and then get uniformly random things out. But that's exactly what we require for a function to be a pseudo-random function. So if we're giving it uniquely unique inputs, then the outputs look uniformly random. So in summary, I have this framework, or we have this framework where we can do composable security. We have these various attack models, and we can use string diagrams to do things. And we're also working on extending it to capture these other frameworks for composability. And we even have ideas on how to model sort of non-composable game-based security in cryptography. And that's it. Thanks.
In that last example you gave,
Yeah.
I noticed that the F1 stayed the same all the way through. And
Yeah.
also in the previous slide, you didn't explain how the invertibility worked. So do you actually need 3 rounds, or can you do it with 2?
Good question. So, okay, I'll mention. So one is that seemingly, so I clearly use F2 and F3 being pseudo-random functions in this proof, but F1, I seemingly don't use it. Well, actually, it does get used in proving this lemma here. So it is needed in this proof. I don't remember off the top of my head, but there was this subtleties. So you could do this sort of, generally you can do sort of an n-round version of this. And I've forgotten the basics, but I think there were some surprising things where n was like 2 or 4. So one of these fails to be secure actually. But I could be misspeaking now. But anyway, so there's a good reason why people usually use this 3-round version.
I think we have a question online.
Hello.
Hi.
Hi. Yeah.
Yeah.
Okay. Yeah. So very nice talk. Thanks very much. So I've got a question about how you would model a particular scenario in your system. And I'm asking because I think it could model it, but I'm just sort of interested in the details.
Sorry, I wonder if we can get this a bit louder. It's hard for.
Oh, sorry. Hang on.
I can repeat to the audience, but I'd like to hear it myself.
Okay. So it's going back to where you were looking at the one-time pad.
Yeah.
Yeah, you mentioned that reusing a one-time pad is insecure. But I didn't sort of see the details about why it was insecure. So essentially the idea that if you take 2 messages encrypted with the same one-time pad, you treat one as though it's the one-time pad for the other message, and then use a frequency analysis on the results, as though it's a simple substitution. So I guess my question is, can you model that sort of thing in your system? Because it looks like a categorical transformation from one protocol into a significantly simpler protocol. The idea of using the output of one as the key for another. Is that something that could be done?
I see.
Do you mind repeating?
Yeah. So roughly, if I understood right there and heard right, the question was about the one-time pad case. So, I mean, I just made the claim that you can't just reuse the keys. Now there was a question of like, well, what if you could, I mean, can't you use the, because the sort of ciphertext looks uniformly random. So what if you use that as your sort of key for the next round? And if I'm not wrong, I believe that's also insecure, basically because then, I mean, well, so for example, so I think you can use then the 2 messages after each other to infer something either about the messages or the keys. I need to sort of go back to, I mean, compute what the XORs are, but it's not quite as simple as sort of reusing the message as the next key, or sorry, the ciphertext as the next key. So you do need some more work, for example, the pseudo-random generator I mentioned. But generally, yeah, I guess the whole idea of this kind of composable security is that you could break protocols into parts. So one-time pad is sort of the heart of encryption, and then the other part is juggling questions like how do you get the keys or how do you extend the keys and so forth in a secure manner. I hope
Um,
that answers the question.
Pretty much, yes. So I was essentially asking whether you could model the cryptanalysis of using a message that had been two messages where one had been encoded, where they'd both been encoded with the same one-time pads. But yeah, I think that answers the question anyway. Thanks.
Right. So yeah, just to recap, this more or less answered the question. Let's right. And any other questions?
Okay, cheers.
Hi. There is what my family and her thought is titled Typing Tensor Calculus in two categories.
I have to state my setup because they need to hear me.
It's better if you
Okay.
can, yeah.
Okay.
Yeah, 1 second, I need to share. Where's the, okay, it's no longer sharing, my bad. Let's see if we can get this. Can we see you? I'm just trying to see if we can see you. I think we can see you.
Thank you. Okay. So yeah, so I want to talk about the typing tensor calculus in two categories. And I really don't assume any background, but if there is something that I'm assuming, just like feel free to stop me and then we can just go through that. So I mean, if you wanna like have like Marty says, so if you want to have only one slide from the talk, maybe that's the one slide. So what you want to see here is that if you have a n category, then the n morphism of n category are tensor of rank to n. So that's the general picture. We already know about the typing of matrices in category. I'm going to show you typing of tensor with 4 indices in 2 categories. And the idea is that you can extrapolate to n categories with the same structure. But then you have to define semi-additivity, so on and so forth, that I'm doing here for 2 categories. So, okay, why I am interested in this work, or like in general in this project, because we know that tensor calculus, or like linear algebra, appears in many fields, right? Machine learning, physics. And then the problem with the traditional notation of tensor calculus as it is very index heavy, right? So for example, if you have 2 tensors and each of them like a rank m and n, then if I want to do just a multiplication, right, I have to keep track of a lot of tensors, but I also need to make sure that they type check. So if I want to do this multiplication, your first task is that to make sure that this number of indices matches together, then you start doing the whole machinery that you have for multiplication of tensor, right? But then the categorical type of tensor just offers you this abstraction at this index tree because it's already type checked when you are composing two arrows, right? So you don't need to keep track of indices in principle. Okay. And then what do I mean by typing? I don't mean like a typing in the sense of like a Martin Love typing. So when I say like type system, I mean that I'm working with system that if there is some operation, there should be some rules, and these rules are just being type checked. And if I'm talking about untyped system, so for example, if I'm talking about a type system, if you have a number and then a logical proposition, you cannot concatenate, right? But if you are talking about a non-type system, untyped system, so it's more flexible and you can do in principle anything. So if I brought an example, right? If you are working in JavaScript, and if you have a string and a number and you want to concatenate them, so in principle, JavaScript assume that the string are more fundamental type. So it changes the number to a string and it just concatenates it as a string, right? And it doesn't raise any error, right? So we are interested in the first type of systems. So one clear example of this is the category of matrices. And it's good for typing in general linear algebra, right? So the object of this category are natural numbers. And then morphisms are just some arrows that the domain and codomain determine the rank of the matrix. So it tells you that how many columns or how many rows your matrix, right? And then if you want to do the composition, then it's just you are the multiplication of linear algebra is that you are doing the composition of arrows in a category. And because it's in principle type check, you don't need to keep track of all indices, right? So that's the basic example in categories, and we already know of this example. Okay. But one important aspect of this approach is that it gives you also a categorical way for vectorization, right? So if you are working in if you are working, for example, in machine learning algorithm, right? So usually the people say that let me show you something. Maybe it's better than like going through abstract. So if, for example, you have a convolutional neural net, right? So usually people tell you that at the end of the, your network, just transfer everything to vector, right? Or in each step, what you are doing is that you are doing a lot of max pooling, which actually changes the size of the matrices that you have, right? It's the form of vectorization, right? So the good point of this categorical approach is also it gives you a categorical way for vectorization. So what do I mean by vectorization? I mean that if you have a matrix F, then you can just write a column, point a column matrix or vector after. But then if you check that, like if you think of it in a categorical sense, what's happening here is the following. So you have a map that it goes from 2 to 3, and then you get a vector that's from 1 to 6. And if you know a little bit of a category theory, it's sort of carrying, like it seems to us it's some sort of carrying map, right? So maybe just like a carry or correspondence actually captures the essence of vectorization aspect. And also that's the important part of this, structure. Okay. So the category of matrices is just a simple example. But if I want to generalize that to a more to a general category, then the structure is going to be a semi-additive monoidal category. Okay, so what is a semi-additive monoidal category? I mean, well, you probably know a monoidal category is a category that is equipped with the bifactor tensor, right? And these bifactor tensors have, okay, you also need a natural isomorphism alpha, and it's satisfied a pentagonal and hexagonal equation, right? But you also need the semi-additivity here. And both in a categorical sense and also in two categorical sense, the way that I'm defining both definition is the strong version. In a sense, I am assuming that I only work with zero morphisms. I mean, if you check the paper, you can see that you can start from a more general setting and start from constant morphism and go on and then define a two categorical version, just to let you know that there is also a more general version for that. So an object is a zero object if it's both initial and terminal, and morphism that factors through the zero object are zero morphism. Now, the first definition that I'm going to give you is the algebraic definition, and I want to give you an addition between objects with this algebraic definition for biproduct. So what I assume is that home sets are commutative monoid. Then a byproduct of pair of object is a tuple. So this is the byproduct of two objects. So you take two objects, and then you have projection and PB, and you have two injection. And this morphism satisfies these five equations. Okay. And then so IA, PB are identity, and the combination of them gives you zero morphism and this master equation. Okay. So this is the algebra. Let me also tell you that what I'm doing here. So the work. So what I'm doing here is the following. So I started from category of matrices, right? And I told you that this is suitable for linear. Right? Then the idea is that I want to go into a more general categorical setup, and this is going to be a additive. And then we go. And I want to play the same story here, but now instead of thinking about the matrix over field, I'm talking about like a general matrices that their entries is basically some morphisms, right? Some morphisms. And then in both this setting, I want to define what is vectorization. Okay. But to define a semi-additive category, I want to tell you that what's the sum between two objects, which is basically the definition of biproduct. Okay. But then, if you check the literature, there are three types of definition for biproduct. You have the algebraic definition, meaning that I give you some equation, and then the second definition is uniform definition. Okay.
I can go.
Yeah. So, so this is the categorical setting, right? And in the second part, I want to go and do the same for two categories. Okay. I'm going to copy and paste everything to two categories. Okay. But then what's missing here in the two categories is that, so that I already have the example, which is the category of two-way. And then I want to switch to semi-additive monoid two categories. But then these two are missing from the literature. So these two, I'm going to define that part for you to be able to have this structure, right? And then from this structure, then I give you the same, the same machinery for typing matrices, but now you can also use that for typing matrices
and tensors. And then from there, I'm also going to define the vectorization form. That's the general picture of the talk, right? So if you are getting lost, you can always go back to that map. And then, so that's the first definition is the algebraic definition that you can see that. Now for the second one, just because when I go to the two categorical case, it's good to have it's good to see the for two categorical case, it's good to see the categorical case as well. So the definition of limit form tells you that if you have a coproduct and product of object, so there is a canonical map R that satisfies PK, R, IJ, delta KJ, and delta KJ is on 1 when K and J are the same, and 0 if they are not the same. Okay. So in a limit form definition, when R is isomorphism, then you have a biproduct of R. Okay. So it means that coproduct and product are isomorphic. So now one needs to show that these two definitions are equivalent. Okay, so starting from algebraic form, you can get the limit form and vice versa. And we have to do the same in the two categorical cases. So if I start from the algebraic definition was the definition that I gave you 5 equations. So what you need to do is that you need to only show that P, the byproduct and projection, is a product, which means that it satisfies the universality condition. And then you want to show that P, IA, and IB is coproduct. So again, satisfy universality condition for coproduct. And it's easy to show that. And from the limit form, starting from the limit form, finding the algebraic form means that you have to show this map. I mean, this is a canonical map. You can be from this equation the 4 algebraic equation that I told. And it's easy to see that as well. Okay, but just to have an idea how we want to prove these two definitions are equivalent. Okay. So a semi-additive category is now a category with finite byproduct. And a monoidal semi-additive category is a category that these the byproduct and also the monoidal product are distributive over each other. Okay. So now this setup is enough to define, like to go and then generalize that picture that I told you. Now, if you have a morphism, these are now not, like if you think about the example that I told you, in that example, objects were natural numbers. Now it's just sum of objects, right? And for example, if I say that Fij, so it is a map from AI to Bj, right? And you can increase the form of this map. And when you vectorize it, you get this color, right? So now if you check in this category, you can have more precise definition for vectorization. What's that? So if I have a morphism F, that it is just a matrix from K times N to K times M to N. Okay. For each morphism F, you can define a vector that it is from M to K times N. And it is just a correct, right? And we call K is a thinning factor, like how you want, like how big is your starting matrix and how you want to make it thin, or like how much thinner you want to the second matrix, right? So if it is a 2x2 matrix and then you want to transform it to a vector, this one is 1, right? M is 1, and then you can play the same story. But if it is a more general metric, so you don't need to do that. Okay, it's clear. So, and then the good point about the vectorization is that if you have the vectorization, then, and also if you either from the hardware side or from the algorithm side, you're advised to do like to just transfer everything to vectors, then you can also define other type of operation with vectorization. So for example, imagine that you have, you start from morphism F and want to define F transpose, right? So I'm going to show you just by vectorizing and unvectorizing, you can define the transpose, and it's the only thing that you need. So if I have morphism F, then you can do unvect. So then you can define you can have n times k. Then you can do vect. Then you have n times k. Then you can do another unvect. Then you have a map goes from n to k, and it's exactly the definition of F transpose, right? So the idea is that if you know how vectorization works in a category, which is in this case is just a corridor, then you can define other sort of operation in linear algebra from vectorization. And it's also not by me, but by some other authors. Yeah. So now we're gonna go to two categorical case. So everything that I told you, now I'm gonna show you that how you can build the two categorical case. Okay. So just to remind you, two category, you have object and one morphism between object and two morphism between one morphism. And you have two types of composition, horizontal composition and vertical composition. And I assume everything is a string. So both the horizontal composition is string. So you don't have any coherency condition here. Okay. Now I have to do the same, procedure. So first I need to define the algebraic form of byproduct. And then I need to define the limit form, because as I said, I don't have such a structure as semi-additive two category here. And then I need to show you that these two definitions are equivalent. And this is the definition of semi-additive two categories, right? And you are going to just build everything that you want. So in principle, for limits, you can have like different form of limits, like a strict, weak, lax, or lax. But I'm gonna stick to the weak limit. So I'm going to work with weak limits and dependent and strict limit from weaks. Yeah. So I first define the. Okay, so let me first define the limit form definition of byproduct. So to define the limit form definition, I need to define weak product in two categories, right? So that's the first step. So it's a line list. I don't, I just go through the picture. So if you have if you have two objects in two categories, and you want to define a byproduct in two categories, it's the A times B, such that for any other object X, and morphism F prime and G prime, there exists morphism D prime, such that these two triangles commute up to two morphism and psi prime A and psi prime, right? So the difference with the limit form is that this is not unique, right? So, and also you have the commutatively of these triangles up to these two morphisms, right? And then the second part is that if such a coin exists, if this blue coin exists, then for any other coin, the red coin, right, with the same condition, right? If you have two morphism F and G such that these two triangles commute up to the two morphism psi A and psi B, right? Then now the universality condition comes here, that then there exists a unique map between these B and B prime, okay, such that it satisfies the following condition. That's the whole definition of big two product into categories. Okay. So such that for PA gamma, and then you can see that actually in the picture, because if I show you the picture, basically the idea is that if I have PA gamma, then it is equivalent of the composing of these three lines. So I'm starting from here, sigma A composed with sigma A, and then Hesi from A minus. Does it make sense? Right, okay, so that is important because that's the condition is the most important part. Just remember, because that's the way that now we're gonna define the byproduct. So I need to, I need to structure, because when I define semi-additive category, in both settings, I assume that home sets are mono. So what is the correspondence here is that here, home categories are semi-additive. With the definition of semi-additivity that I gave you in the category, right? So you are starting with the two categories, that home categories are already semi-additive. Okay. So now, yeah, I defined a locally semi-additive two categories, a two category whose home categories are semi-additive, right? So they have finite byproduct based on the definition that I give you in categorical sense. Okay. And then the second one that I need is that a locally semi-additive and compositionally distributive two category is a locally semi-additive two category whose two morphisms composition distribute over. So if I'm in a home category and it is semi-additive, in the home category already home sets are monoid. So then what I require is that the horizontal composition distributed over the addition, and the vertical composition also is distributed, right? I also need this. So that's the setup. Now the definition of byproduct. So the definition of byproduct, obviously, I mean, and now because I'm in a two category, just remember the notation. So in a categorical, okay, if you go back in a categorical case, I show byproduct with this is not the with a circle circle add, or what do you call it? Circle sum circle? I can't remember in the latex. What we call it. And now here is box sum. So you have a box sum within object. And you have a set of projection and injection, and they are one morphism. And then you have a set of coherency two morphisms that I call them thetas. And we will see what are they. So basically, I mean, projection and injection is the same. So you have, if I have the byproduct of A and B, so projection maps byproduct to each of these objects, and injection the same. So if I have the injection from A to A plus B and the same. But then the identities that the equation that I told you in a categorical sense is only in that sense, in the categorical case, they were all equivalent, but now they are isomorphic, right? So you have PAIA isomorphic with identity A, and then so on and so forth. But then here also the case that if I have PBIA, it's not the same as zero morphism, it's just isomorphic up to these two same. Oh, sorry. And then the same, the same for theta B. So that's the important part. So what I showed, okay, so the conditions are important because if you remember in when I start from the weak two product or weak product in two categories, at the end of the day, I have a condition. And this is basically, these two conditions captures the condition that I showed you in a weak two product. Okay. So you can define the limit form here. I don't go through the limit form. And then you can also prove that these two definitions are equivalent. And actually can go through the proof as well, but they exist in the paper, you can check it. So now what I have here is the following. So you have if I have semi-additive two category, right? So I have two product at the level of zero morphism with one morphism projection and injection. And each home category is also semi-additive, right? And I have a projection and injection in each home category as well. So you have to imagine that you have byproduct between object and byproduct between one morphism, right? And then you have a two morphism projection and injection, and then you have one morphism projection and injection as well, right? So it's like it's happening in two different levels. So now if I'm going back to the title, right? So I want to show you that this setup, semi-additive monoidal two categories are suitable for typing tensor up to 4 indices, right? And that's the example that captured that. If I have one morphism, right? The two category with this byproduct as Bart's class, then in principle, if I have two morphism between F and G, I can actually factor it in the following way, right? Sorry. Oh yeah, just one slide. Okay. And after mommy's break, right? Okay. So that should be fun. So each of these F and G in principle can have further components. So for example, if I have Fjk is a morphism from Aj to Bk, and Fjk in principle can have the further component, because remember, they are living in home categories that you also have a byproduct for those, right? So in principle, this one lives in a home category that it is semi-additive. So you can in principle have further component for each of these morphisms. And when I say theta Jk is a theta component between these two morphisms. And then you can further expand that with a two morphism projection and injection. And it gives you two other indices, right? So if you check the picture, it gives you the best view. So in principle, this is the 4-dimensional theta, right? So if I inject it along with the fourth dimension that you can see, then I get a cube, right? So it's like you are in that level, you first inject it with the one morphism injection, you get a cube. Then you project it with one morphism, then you get the S-square matrix. Then if I, again, with the two morphism projection and injection, I do the projection and injection, then I get one entry of that matrix, right? And now it has these 4 indices to describe. Yeah, and that's the essence, right? And then the first part is actually to define to have the first part. You need the semi-additive structure in 2 categories, and this part is actually just the categorical case, right? Because you are this is now after the first projection and injection, now you are living in a home category. And these are the semi-additivity definition for categorical case captured this part, right? So now this is important because, and I know that I'm running out of time but it's the important part because now you can also in principle have 2 types of carrying. So external carrying and internal carrying. So what the external carrying do is that if I have F and F prime and theta between them, so the first carrying, which I call external carrying, just map everything to vectors, right? So you have V for F, V prime for F prime, and alpha for theta. But then this theta, and this is the picture of carrying, so I don't go through that. I just finished the example. This alpha, which is a vector, but each of the entries of this vector can be principal matrices, right? Remember the picture that I showed. So now you need another carrying here or another vectorization, and it is a second vectorization that sends that matrix to a vector. And just stacking these vectors in home category on top of each other. right? So this is the second query. And then, yeah, so this work, like the second part of the work works in this setting, we are working with semi-additive monoidal categories. Now we are thinking about the Cartesian closed by categories, and then having a more general definition of query forward in Cartesian closed by categories. Okay. Oh, sorry about it. Yeah, that was that. Yeah, sure.
I work in machine learning, and I have a class of problems that could be solved by a generalized inverse. But we'd like that inverse to be an injunction. Do you know what the injunction?
That's actually
of the two
interesting.
category might look like?
Yeah, I don't know that, but it's something that I'm also thinking about. Yeah, because yeah, exactly as you said. Yeah, so you need to also adapt the inverse of tensors, and then you also need the adjunction for that level as well. Yes. Yeah, but I don't have an answer for that at the moment.
Right.
Thank you very much.
Thank you.
Probably break outside for about half an hour. Just be talking together for a group picture in front of the building while it's moderately sunny.
Oh, but well, at least we hear it from there, which is
Oh, okay.
thanks.
Keys, I guess.
Yeah, just
Jamie, I was surprised that you weren't joining us. I was like, this is James Hartley, and then the host is not here.
Well, we're talking for half an hour or 25 minutes. Then we get to 25, I'll say 5, meaning.
Okay.
to the end of the
Yeah,
session.
I'm also trying to try and keep going.
Oh, yeah,
So,
yeah.
if I look at it, if I don't, then. But
Okay, hello everybody. Welcome to the second session of second day of SYCO. Well done for making it to the second day. And so we've got our first speaker, Tiffany Deneau from Continuum, and she's going to talk about compositionality in NLP, generalization and interpretability with discourse.
Thanks. Yeah, so what I'm going to be doing is giving you a bit of an overview of how you can use compositionality for natural language processing. So specifically, it's two properties, compositional generalization and compositional interpretability, which I'm going to kind of give a bit of an overview of via the lens of like a particular model, which is DiscoSerg. So to give an overview of the task, we have some story and then a question about that story. And our goal is going to be to build a model that can solve this task. But the one extra thing that we're given is some set of rules that tell us how to break down the stories into some component parts and then rearrange them to make more stories. Maybe they're longer, maybe they're just like different commuted around. And so the kind of key bit of the compositionality is that these tasks have this underlying structure that we can try and use to like help train our model or help do things with our model. So kind of to give to frame like what this compositionality stuff is, we're going to do it via a grammar. So I'm going to present it to you as a DiscoSerg grammar because that's how we're going to then apply it later. But it could be a bit more general than that. So the kind of basic setting is some monoidal category where you have some objects which are going to represent the nouns in our story. And then the other words are going to become processes that modify these nouns somehow. And then the kind of shape of the box is going to depend on the grammatical type that we assign to that word. So if it's an intransitive verb that applies to just one noun, it's going to have one dangling wire on the top and one on the bottom. For transitive verb that has two dangling wires. The other type of thing we have is these thing called frames. And I've made it a ish monoidal category because how exactly we specify them is to be determined or up to some stuff. But for now, you kind of don't need to worry about it too much. You could consider it as like, if I can bend these wires down, if my category is closed, then I can express them as just boxes, or later on, I'm just going to show you another way to expand these out as boxes. So just kind of view them as they're higher order processes that can take an input. They want to take a box, so they're kind of modifying other boxes, like an adverb modifies a verb. But they're just kind of another generator that we have that we can build diagrams from. So these are the kind of building blocks. And then when we want to make a sentence, we can kind of put these together in certain ways. And the particular way in which we can put them together is guided by the grammar of a sentence. So in the first example, like Bill moved to the kitchen, Bill is the subject of the kind of the move to frame. So we kind of plug it into the subject dangling wire of the frame and then like compose it into a sentence like that. And we can do this with various sentences. And the grammar is telling us how to plug things together. What we can also do is there's kind of like grammatical rules that tell you how to compose sentences together into a story. So the kind of important one here is the idea that we can do co-reference resolution. So that's just recognizing that Bill in the second sentence is the same Bill as the first sentence. So what we did with the two previous diagrams was just connect them along the Bill wire and have the second sentence just like come on afterwards, up to some like kind of like state removal so that there's no like double Bill state. And the wire connects. But that's how we put sentences together. So this is like one of the rules that we have to like recompose the atoms in our task. All right, so to like drive down the point of what compositionality is, we're going to view it as a property of some function that we can take on these diagrams. So this function might be our model, or is like just the task, like something that solves a task for us. And it's some function on diagrams. And compositionality tells us that we can break this function down into how it acts on each of the individual components of the model. And then like combine these in terms of some like operations that like mirror how we compose the original diagram together. So here I've like put 3 operations, including the like put into frame operation. That one might not exist. But this is the like picture of what compositionality means. But that's not necessarily useful by itself, because you could have like very generic like atoms. So it's like it's not really telling you that much useful. So what we really care about is there being some specific rules or like ways to get from a certain set of stories to another set of stories, so that we can kind of build models that can take advantage of like this way of recombining things in the first set to make the second set. So one of the ways that we're going to look at here is called productivity. And there's some other ways as well, which I'm not going to go into detail, but you can, yeah, check the paper or something. So productivity is basically this like co-reference resolution between sentences. So it's if you have 2 small sentences or like small stories, like you have on the first side, you can combine them into the one in the middle. You can't really see the orange, which is unfortunate. But the Bill wire here is like highlighted because that's where you join them. And there's a rule that tells you can do this with like any small stories to make a bigger story. So the idea with our models is that if you train it on only the small stories, and it knows about the rule for composing small stories into big stories, then you don't need to train it on any of the big stories in order for it to get the correct answers on them, provided it's getting the correct answers on the small stories. So this is kind of like what we want to be testing in this situation. And the way we're going to kind of do that is with this metric called a compositionality score. So this is just combining this idea of like, you get a good score on the test set if you also got a good score on the train set into just one number. In this case, we're considering A to be the easy small stories, and then B is a data set containing only the bigger stories. And what we want is if it has a high accuracy on A, the compositionality score is kind of penalizing it if it gets a lower accuracy on B proportionally to like by how much the accuracy dropped when you go to B. And yeah, in this case, we're looking at tasks where it's a binary task, so there's only 2 options. So the kind of baseline is 50% accuracy. So yeah, we see like this like white line is 0.5. So you can see like if it's getting 100% accuracy on A, it's going to penalize really severely with like a bit of like even a slight drop in accuracy on the B data set, because the idea is like we at the cost of like we'd rather have it match accuracy on B to accuracy on A than be good at A only, because it's kind of capturing the idea that if it's compositionally generalizing, it should be like maintaining accuracy. Okay, here's a like kind of view of like how we're splitting the data that we're going to be training on. So the compositional difficulty in this case, because we're doing productivity, is just the number of sentences in the stories. So with the training set, we're doing the short stories, the test set is the big stories, and our validation set is kind of overlapping both the train and test distributions, but not the actual stories, in such a way that we can compute this like compositionality score from this, like from the validation set, so we can select our models. Okay, so a bit more detail about how exactly we're solving a task. I've told you how to get a diagram from a story, but our tasks had questions in them. So how do we like answer a question? The way we do this is with this thing called assertions. So each question has two possible answers, like yes and no. And what we're going to do is generate a sentence that expresses like the kind of, expresses the answer to the question in a full sentence. So Bill is in the kitchen, as opposed to, just yes or no. And then from these sentences, we now know how to convert those into diagrams using the same rules as the stories, because they're just statements now, and we get a pair of diagrams. Then the next thing we have to do is add like one small extra thing to our category, which is a notion of daggers or adjoints, so that we can compare two diagrams. So we just plug them together, flip the assertion upside down, and then plug it into the bottom. Maybe discard like any extra wires. And then this gives us a number that's going to represent the magnitude of the overlap between the assertion that we want to check and the whole story. So the answer to the question is then just the assertion that has the highest overlap with the story. Okay, so that was the task, but so far I've not really told you how to make it a model yet. We've just got like pretty diagrams, and so we need our F. We need to kind of define what category we're going to like take it, make it be a functor 2, so that we can get actual numbers out. So there's kind of two ways I'm going to look at here. The first one is a quantum interpretation. So we're going to make the whole diagram a quantum circuit, a parameterized quantum circuit, so we can train it. Because quantum computers don't have that many qubits, and also we don't have that much memory, we're going to restrict ourselves to just putting 1 qubit for each wire, so we can actually train and fit these instances on the machine. Then all the states we're going to like just plug in with some zero, like initialize it in some computational basis state. Then we can parameterize any single qubit gate using this Euler decomposition with 3 rotations. Then any like other gate we can parameterize using an ansatz. Here we're using 3 layers, and it's fairly expressive without too many parameters. That's why we're using it. You might remember that we had these things called frames. So instead of giving you a like direct way to interpret a like box with a hole, we're just going to decompose these using what we're calling the sandwich functor. And kind of the idea here is that we're going to treat everything that's in the frame, like the hole in the frame, as the filling of the sandwich, and then put bread slices around each filling hole, so that like with the like top and bottom slices, so that these are all boxes, like usual boxes, no more holes. And we're going to add some extra wires so that we're not doing any extra discards or like initialization, so like number of qubits remains constant. And then this is just like, we can apply the ansatz we had from before to this. So we can get a quantum circuit for our overall like diagram that represents this task. So that's like option 1, quantum circuits. Option 2, we're going to also look at neural networks. So instead of filling in the boxes with a quantum circuit, we're going to fill it in with some feed-forward neural network. First case is kind of like degenerate, because we're also just looking at if we don't have a nonlinearity at the end. So it's just a matrix. and that means the whole thing is linear. But it's kind of interesting to look at in comparison to the quantum case, because the difference there is in the tensor product we're choosing to use. So it's a direct sum as opposed to the usual tensor product that we would have in the quantum setting. D here is, we do vary that, because if we just picked like one for each noun, then that's like not very expressive with direct sum. So we're treating that as a hyperparameter. Then somewhat more interesting, we have like treat this like flat architecture where we have just a nonlinearity that's applied element-wise after the like matrix, the weights. So this is just like one layer of a feed-forward neural net. We're reading sideways for variation. Yeah, so
becomes the linear. So it follows becomes the neural network.
yeah, so these are three different ways to express. So like there's one interpretation of F where we're just doing only linear, and there's another one where we choose to instead make it this like flat single layer of like neural network. And then we also tried another one which was just 2 layers. So this is like strictly more expressive the more you like go this way. So it's just like to see if that made a big difference. Ultimately, the task that we were solving is kind of simple, and as we'll see, that didn't actually make, well, yeah, we'll see in a second.
Is the matrix M the interpretation of the verb follows?
Yeah, so in this case, so M is like, yeah, some matrix, so we can parameterize that, and that's where all the parameters are. This is just some function, like the non-linearity that we apply afterwards.
It's like a softmax for example.
Yeah, so mesh is like a particular function that looks like a ReLU, like, but it's just smooth, so we can differentiate it. That just gave better properties than ReLU for training. Yeah, so those are like 3 options that we can use for the neural case to train that.
Isn't it a lot to just have neural network for a verb? It's quite a lot of it.
Well, it's a very small one. So as in it's not like the number of parameters is like on say the linear or the flat one is going to be like, it's a D like 2D by 2D matrix or something like that. So it's not huge. Like, well, as long as D is not huge, then the matrix isn't huge. But the matrix for the whole, sorry, the neural network that you get for the whole circuit is then going to be like non-trivial, because you're kind of keeping the same connections that you had in the original disco circle, like syntax diagram. Okay. So back to the task and some results. What we're trying to do is test this compositional generalization thing. So that we train on small instances and then test them on the big instances and see if the model accuracy dropped, or like ideally didn't drop. So just to introduce the plots, I'm going to plot the compositionality score that I introduced earlier as a blob. And this is kind of depending on both the train accuracy and test accuracy. So I'm also just going to plot those so we can see as well what they were, and there's a line between them to highlight the difference, or like the magnitude of the difference. So this is from previous work that we did just studying only the quantum version. On a task, there was like people moving in different directions, and we asked where they were going. So we see here the quantum model does like really nicely. It's in the corner. Did like got 100% accuracy on the training, and then it only dropped to like 95% on the test set. So like the overall compositionality score is still really good. So that's always very encouraging to see. As a comparison, so this LSTM transformer is not the neural like disco cycle that I just introduced. That is literally an LSTM or a transformer solving the same task. And what we kind of seeing here in contrast is like both, they didn't really manage to solve the task very well. That can make more comments on that maybe later, but like maybe not the fairest comparison, but does show at least that the task wasn't completely trivial to solve. And importantly, like especially the LSTM, like the accuracy drops to basically random on the test set. So it's kind of like got a really bad compositionality score because it's kind of really overfitting the training, and it's not really taking advantage of the compositional rules that like the data set underlying it has.
Can I ask you a question?
Yeah, sorry.
These architectures are quite different, right?
Yes.
So how do you ensure it's like a fair comparison?
So yeah, so in this one, it's like not particularly fair comparison. So I think, yeah, like
How so? How is it not fair?
so part of it was like in the training, this one had quite a bit of help to we kind of made some simplifications to the data set that we couldn't translate over to the kind of classical models because they relied on the compositional nature of like discourse. So we could yeah, so there was a little bit of like extra help that got given here, which is why like this being low isn't like you shouldn't take that as like result, right? But like the fact that this was like this drop, that's still relevant, because it's like it could like plausibly could still like I guess this one didn't drop as much, but that was pretty more difficult than anything else. Not obvious from there, but from the rest of the data. But yeah, like in the next slide, I'm going to show you some comparisons which are more fair from the like discourse circ architecture. But yeah, the like splits were still the same, so like there is still some sense in which you can compare. Yeah, so here's just another data set that was slightly harder. I guess the point I'd like to make here is that this is an example of like really like nice compositional generalization, even though the accuracy isn't super high. It's like the train and test scores are like basically on top of each other. In fact, the test score was like slightly higher than the train score. So it's like whatever like rules the models learn, it's applying them consistently like at much larger instances. So it's kind of doing what like this is what we want. But to move on to like comparing the architectures I showed you, this looks, I mean, less less exciting. But the difference here is like, so this is a slightly different task where we gave way less help to the so this like the amount of help that the kind of architectures got is equivalent to the help that the neural architectures got in the previous slide. So we haven't like sneakily helped out quite so much. But what we're seeing here is like the accuracy on the training set is like pretty high, but there's quite a big drop to the test set, which means that the compositionality score is suffering quite a lot. So it's still above the baseline, but it's not that far above the baseline. So yeah, like we might be like, well, you know, can we maybe try and say something more about like why it's like that? Like, is there anything more we can do? And the answer is because these were disco circ models, we can do that with this notion of like compositional interpretability. So before, like the generalization thing is kind of independent of the architecture of your model. So we were able to plot compositional generalization for an LSTM or a transformer that didn't have compositional structure in the model itself because the task had that structure. And the task was telling us how to split the training and test data accordingly. But the interpretability part comes in when our model is also got this structure, because instead of having some big black box, we have from compositionality loads of black boxes. Great. But the important thing is like, so we have these like operations that we know about, so we can just kind of remove those and look at the boxes individually. And also because we're using the same rules to build a model that we use to kind of build a task, we can label all these boxes. So this is maybe helping us already because we have a sense of what each box is meant to be doing. So when we try and interpret them, maybe you can see like that is doing what we think it should be doing. But the kind of main key thing is that we can recompose these boxes because we know what the rules are for like putting things together. So we can get kind of diagram fragments and evaluate those and compare those, and then get an idea of how the model's behaving by just looking at these fragments. So we can understand the kind of overall behavior without having to understand exactly what each box is doing very specifically. So to kind of get back to one of the models, let's look at the quantum one. And like try and figure out what's going on here in the thing. So here's a diagram for argument that we might be interested in. So the task was about people moving to some locations and they also picked up objects, but yeah, so here's like a fragment that we might be interested in. We care about whether Andrew is in the park. So we don't really care whether Clara got there before Andrew. So we kind of might then like put in an axiom that says, well, the model probably shouldn't really care that whether Clara got there before Andrew or not, because they should kind of commute on the park wire, and that should be equivalent to the model for the purpose of solving the task. Unfortunately, if we test those directly, we kind of find that, oh, they're like really dissimilar, and like maybe that's not, so it's not informing us that much, because ultimately the model is not actually seeing these things directly. It only cares about them like relative to an assertion. So instead, we'll upgrade our previous stuff to be considering assertion relative fragments. So we just post-select all our fragments with an assertion. So that was just the like Andrew's in the park or Andrew is not in the park. And then like do the comparison again with the assertion relative fragments. And what we find is, again, well, they're not equal, but like we do find other other axioms that when we test them that like were equal. And then kind of the ones that we found that weren't equal end up suggesting that rather than answering the question, is Andrew in the park? The model is kind of doing something more like, is somebody in the park? So it doesn't actually care who's in the park, it just cares that somebody's there. And kind of the axioms reflect this kind of thing going on. So you might be thinking, well, okay, like let's go back to our like actual data and see if this actually explains what happened. And it turns out if we plot the confounding, which is like the number of sentences in our story where the location that we're asking the question about, like the park, shows up in. And so when the answer is meant to be no, we see that if there's exactly if there's like no sentences in which the park shows up, then the model's correct. It's like, oh, yeah, no, Andrew is definitely not in the park. Like nobody's in the park. So it gets it right. But as soon as anyone else is in the park that's not Andrew, then the model starts getting it wrong. So we see like the drop in accuracy on this like bar plot here. The model is like, oh yeah, somebody's in the park, but it turns out it's not Andrew that's in the park right now. So it answers yes in all the other cases, but like then it just happens to be wrong for kind of the wrong reason. So we've kind of figured out what the why the model is getting stuff wrong. And the reason that it didn't look very compositional was because as you add sentences to your story, you're more likely to have a sentence that says somebody goes to the park and it not be Andrew, or like it not be correctly Andrew. So it's kind of like more and more likely for the model to be wrong the more sentences are there. So if we change our question to is somebody in the park, then the model would like be getting like nice compositionality scores, but obviously that's not what it's doing.
So you go 5.
Yeah, I just like not going to summarize. So yeah, so everything I've been talking about is like relying on this idea of compositionality. The first instance is if your task is compositional, then you can check things like compositional generalization and hope that your model, or like kind of train your model so that it reflects that. The second thing you might have is a model that's compositional. And then if it's the same compositionality as the task, then you can do this interpretability business. And most importantly, you can kind of figure out, given your model, whether it's being compositional or like not compositional for the right or the wrong reasons. And you can kind of understand what's going on. So yeah, I will. Yes, the last thing, Disco Circ is such a model. That's why we did this example. But yeah, anyway, thank you.
Thank you.
So the example of the task that it was doing poorly on, one possible reason that it was performing badly was because there's no explicit way in the model for it to, I guess, deduce that two things should commute with each other, right? That was an equation that you were testing after the fact that wasn't actually in the model. Is there a way that you could add that kind of symmetry to the model?
Yeah, so that's exactly, so when I was saying we kind of cheated a bit, or like not cheated, but like helped out the model in this case, that's exactly what we did. So we knew that there were some symmetries in the task that the model should obey. And we're like, okay, let's build them into the ansatz basically. So we're just like, oh, this gate should be an inverse of this other gate. So instead of learning 2 sets of parameters, we'll just force it to be the inverse. And that made the training a lot easier because it's kind of got some built-in like hints about the task. And yeah, in general, that's something I think we're like maybe looking into more to like see if we can do more of that. And help out.
So you mentioned that your box with the hole is not always well defined.
Well, it's more that it's pending maybe like formal definition. There's so at the moment kind of like got glossed over a little bit like what exactly it means to have a hole. There's like a bunch of available like ways to express that. I think there's like lenses or like higher order maps that people have come up with. And then
You work in the Monoid.
yeah, so the kind of ideally we want it all to collapse back into a monoidal category. So at the moment, like I guess one of the ways to get around this higher order thing is to do the sandwich functor idea and just like expand it as just like the sandwich layers.
And then you need motion. Like,
yeah, so yeah, it still has a hole, but like once you've composed it with other things, the hole is filled and it's all fine, I guess. So yeah, there's a little bit of a like hand wavy moment where I'm like,
okay, no, but I think there is a way to formalize.
yeah. So yeah, we're like I think working on it, like doing that properly, but yeah.
Can I check my understanding before I ask a question? When you have these diagrams, choose a vector embedding with the diagram, with neural networks are being trained. Is that the case? And when you are composing sentences, you're composing through addition in the neural network case.
So we're not going like making a vector embedding of this that we then feed into a neural network. We're converting this into a neural network. So like each of the boxes is going to be like some small layer of the neural network. And then they're going to like, so it's not going to have all-to-all connectivity, which is the usual situation. We're going to remove some of the connections and it's going to map the same like the connections of the diagram.
Last question from Jamie.
So yeah, it's a question about how this work relates to other approaches. So attention-based, so you compare to a transformer model here. I'm not sure exactly what architecture that is. Conventional attention-based transformer models obviously can learn extremely rich features of their training sets. And I presume that includes some sort of structure we call compositional structure. So is that something that you looked at? Would you propose that this sort of approach can in principle learn compositional structure, which the dominant attention-based transform architectures can fundamentally never learn? For example, you making a claim, I haven't heard you make a claim like that. Is there some reason to believe that's the case, or not? Maybe it's the case that attention-based transformers can already really learn these types of.
So I think there's some amount of literature suggesting that it's hard for transformers to learn that. I don't know that it's like impossible. I wouldn't claim that. But definitely it's not trivial. And like I guess the experiments that like the results I was showing is I think I would take to state more like it's not trivial and it's like it takes some effort to get there.
Yeah.
And the idea is that if your model has this compositional structure, it might take you less effort to get there.
I mean, the test
but it still takes
if we ask ChatGPT, it would probably solve them.
Oh, well, so interesting, funny you should ask this. But so we did at the time, and initially, like when we started this project, it was actually really bad. It like couldn't solve it. It was getting, yeah, like basically random guessing accuracy. I think now it probably could solve it, but it's not, yeah.
So what happens in ChatGPT translates it to code, and then Python obviously solves it for you very easily. Because the logical puzzle isn't. These are the features that have been added. Anyway, final speaker again, lovely for example. Okay, second speaker has come all the way from New York. And his name is Jake Simon. And he's going to talk about composition nonlinear audio signal processing with Volterra series.
So thanks for the invitation to speak. I'd like to tell you all about this model from signal processing called the Volterra series, which is a model of nonlinear systems, and kind of an attempt that I made to give a categorical treatment. So just as an overview, I'm going to assume most of the kind of math of signal processing, but I'll just at least introduce some terminology, give some background, and introduce kind of the classical definition of the Volterra series. Then I'll kind of begin the process of this categorification, in particular, introduce some base category over which the Volterra series will then live as a kind of endofunctor. And I'll introduce also a notion of morphisms, morphism of Volterra series, and which will then allow to give a definition of a category of Volterra series and their morphisms. And if I have time, I'll mention just at the end a little application, some application to time frequency analysis. And as a disclaimer, I won't cover the main thing that Volterra series are used for in the literature and applications is nonlinear system identification. So you have some circuit, unknown circuit, you have some behavior, data about its behavior, you'd like to model it. And also more recently, people are building neural networks using Volterra series. But this is quite recent, and I won't talk about either. So, okay, just to. Oh yeah. So in the most kind of conventional or like model in signal processing and linear signal processing is this notion of a linear time invariant system, and the idea is that these systems are one-to-one with kind of convolution type operators. So just to kind of give the terminology that's used in signal processing, lowercase v here is referred to sometimes as the kernel function, or also the impulse response of the system. This is a model of a system. Oh, and I should say that such systems commute with translations, right? Actually, it should be better called shift equivariant systems, but people say time invariant. And the Fourier transform of the impulse response is called the frequency response. And a kind of the key property of these systems is that they can't add new frequencies. They act essentially as Fourier multipliers in the frequency domain. So they're just scaling and maybe imparting a phase shift to existing frequencies. You can't get new frequencies out. Yeah, and just to remind you, the Fourier transform in 1 and n dimensions, and here are some images of so-called Fourier pairs. Not particularly important, but there's some nice properties like inverse bandwidth in the 2 domains, or reciprocally. So yeah, and then just convolution and multiplication, and are related by the convolution theorem, right? Which says that the Fourier transform of the convolution of the signals is equivalent to the inverse Fourier transform of the product of their spectra. Okay, so the Volterra series is a universal model of nonlinear systems with what is called a fading memory, which means that the influence of kind of inputs to the system in the distant past falls off asymptotically on its behavior, the influence on its behavior in the present. And they kind of roughly have this form. So they're given as, and I'll show this, I'll kind of define this on the next slide, but just intuitively, they're given as sums of these homogeneous, what are called homogeneous Volterra operators in each dimension. So this is some kind of graded thing. And concretely, so I mentioned they're giving us the sum of operators. You can think for now of this space and this type S of R just as the space of complex value signals. I'll define it properly later on. And the output of the jth one of these operators is given on the bottom here as what is really a convolution between this kind of like higher dimensional impulse response function, or like a higher order kernel function, the lowercase v sub j, and a product of the input, a kind of j-fold product of the input signal that's being sampled at different delays. These tau variables are delays. And this is really this is actually a convolution between the tensor power, the jth tensor power of the input signal and the kernel function, which you then slice along the diagonal. You evaluate it along tuples of the form t, comma t, etc. And the supports of these V sub j's somehow reflect like the memory of the system, though in each dimension. Although they also have weights, right? And you can write this actually more nicely in the I think in the frequency domain. Well, they have different affordances, but in the frequency domain anyway, you can write it as so. And by the projection slice theorem in Fourier analysis, which relates kind of the operations of slicing and projection, the output, the spectrum of the output evaluated at a given frequency omega here is now given by actually integrating on orthogonal hyperplanes. So hyperplanes orthogonal to the diagonal. So these are defined by equations of this form. So you have this restriction, and here really you just have a product of the tensor power of the signal, the jth tensor, and the kernel function at that order. Yeah, and here's just the writing it out with using the tensor power, and so we have this diagram. So if you start in left hand on the bottom left with the signal, you pass first to the Cartesian power, then the tensor power, you then convolve and slice along the diagonal, and that gives you the output. And so the key idea here is that, and this is evident more when looking at it in the frequency domain, is that the Volterra series is essentially kind of modeling nonlinear effects as arising from kind of, well, it's acting as a filter on the so-called intermodulation components which you get when you multiply different frequencies. And the first order Volterra series is just a linear time invariant system. And so that's kind of the mechanics of how the Volterra series works. I've told you that I can represent different systems. So here are a few types of systems. The first two are linear, and so they are defined just by their first order kernel functions of their Volterra series. And these are well known in signal processing. The delay in the Fourier, I'm giving the kernel function in the frequency domain. For the delay, for example, you have this complex exponential weighting factor, and then so the differential integrated differential operator, and then the memoryless polynomial, which is somehow like the simplest, maybe a nonlinear system, is given just by a constant function in the frequency domain or multi-frequency domain. And so, okay, let me see if I can play some kind of little audio. This is not, I should disclaim, this is not very exciting audio. But so here's my friend Gabriel playing Mary Had a Little Lamb, and here's it passed through a third order Volterra series with just constant kernel function. So you're just generating all possible, okay, so what is it doing? Let's see if I can get that. It just generates all possible harmonics that can be obtained as sums of three frequencies from the input spectrum. And so if you pass through it, for example, a signal comprising three sinusoids, you get some proliferation of harmonics, as shown on the right here. And their amplitudes are given actually by certain multinomial coefficients, just corresponding to the number of ways you can obtain them as sums from inputs, frequencies of the input. And actually the number of peaks that you get, or the harmonics that you get, is here given by the number of weak compositions. Here, weak three compositions of the number three. Because there were three frequencies in the input, and I'm using a third order Volterra series. Okay, so now let me tell you about the kind of attempt at categorification that I made. So the high level idea is, I'm going to introduce a base category. The high level idea of this is that the objects here are signals. In fact, there are kind of two categories related by the Fourier transform, but anyway, the objects are signals, respectively spectra, and morphisms are what are called convolutors. And the Fourier transform is well defined kind of in this category, or on this category. And and by the way, I'm using a different script here. It's just laziness, I'm sorry. This is the same S of R as before. The Schwartz space, but but it's usually just as a space, the Schwartz space is a space of kind of rapid functions which are rapidly decaying. At infinity, they fall off faster than any polynomial. And then the dual of the space is space of tempered distributions, which are somehow like slowly growing, have polynomially bounded growth. And yeah, the Fourier transform is well defined for tempered distributions. I think it's actually like the largest space within of distributions that it is well defined for. So in the Schwartz space in particular, we don't have certain things we would like to do signal processing with, which are, however, the tempered distributions. In particular, we have the delta function and its periodic extension, the delta cone, the Dirac cone, which allows us to do, for example, a periodizing function signals by involving them with it. The space, so those are the objects. We want to introduce now morphisms between signals. So the space of multipliers is the space of distributions that take Schwartz functions to Schwartz functions under pointwise multiplication. And the space of convolutors is basically the same thing. Well, so here's the definition. You have to be able to construct them as sums of derivatives of these continuous functions, but the idea is that they are likewise the convolution type operators that take or maps that take Schwartz functions to Schwartz functions. And the Fourier transform is a bijection between these two spaces. So now we can define this category as S prime of R, which has as objects tempered distributions and as morphisms convolutors between them. And it has, maybe to note, it has a kind of filtered structure in the sense that when you convolve something, the spectrum of the image is also always less rich than that of the source. So it has this kind of filtered structure, and the terminal object should be then the zero signal. Okay, going on time. Let me now, tell you about the Volterra series as a functor. So to motivate this, we can ask, what happens if we apply one of these morphisms in the base category to the input to a Volterra series? How does it change the output? And the idea that I'd like to propose is we just apply the morphism to each copy of the input signal occurring kind of at order j. And I think you can kind of think of this either as pre or post composition because convolution is commutative, but you ought to think of it as post composition. Equivalently, so just to be clear, we have this input signal which is occurring kind of j times on the right hand side, and we're applying L to it, and this will give some output. L here is the convolutor, right? So then in the spectral domain, this is equivalent to filtering the product of the tensor power of the input spectrum with the j-order frequency response function by what is by this gamma, the tensor power of this gamma thing, which is the weight function of the multiplier m corresponding to the convolutor L. So now we can ask, does it respect composition and identity? Is it functorial? And you can kind of see that it is, which basically follows because the tensor power of the Fourier transform of the composition of these two convolutors, which is equivalent just like multiplying their weight functions, is equal to the product of their tensor powers. So it kind of follows on the nose. And of course we have identities, which is which is just given by passing the delta function convolution by the delta function through. There is, I think, however, a caveat, which is that unlike in the linear case, in the nonlinear case, you can get destructive, and you can have destructive interference. So if you try to just define kind of what should the weights be that will transform the, if I wanted to define this map as a multiplier, what should the weight function of it be? if you just try to do it naively using this formula, you could have something where you had cancellation at, let's say, in a second order series between two frequency components, and then you shift their phases and they no longer cancel. And so this is not horrifying.
I can ask a clarification
Yeah.
question. Apologize. So B is the pointer that distorts the original signal. Yeah.
Yeah.
And what are the hats?
These are, this hat denotes the Fourier transform. Sorry, I should have said it earlier, probably. So L of S is the output of, or is the result, is the image of S under this convolution type map L. And then if I take a Fourier transform of that, that's its spectrum.
Is B an endocounter or?
V is an endopuncture, yeah, on S prime of R. Okay, so now we can consider, okay, just some examples of like the images of certain, well, transformations under the Voltaire series. So here are a few kind of classes of transformations in signal processing. And I'm not going to go through any of these examples too much, but translation, as you would maybe expect, translation, it just commutes with V, because V is basically convolution type. It's like a generalized convolution operator, so we would expect that. Modulation is a little more complicated. I don't claim to have super great intuition actually for some of these formulas. If the input signal is 1, you get out something which is like the J, at order J, you get something which is like the J harmonic of the frequency that you're modulating by. And more generally, you end up having a product of this form, but you're actually performing a convolution than the spectral domain if you modulate in the time domain. And yeah, these periodization and sampling formulae, you end up getting just these kind of multinomial coefficients out front, and I can't claim much to provide you with much information, intuition beyond that. Okay, so now so the Voltaire series then is like a model of a system, which is also functorial in a way, but systems change, so we'd like to be able to model this. And so I'd like to define propose a notion of morphism of Voltaire series. I have to just introduce a notation. So, and for anyone who might be familiar with some kind of work on polynomial functors, in particular by Spivak and Yu, this isn't quite analogous. And I should have said maybe earlier, the Voltaire series are very much like polynomials in a way, yeah. So anyway, I first need to decouple the order of nonlinearity from the index of the operator. So I'm just going to refer. So previously I've been using this J index to denote both. I'll just use this bracket thing to denote the order of the operator at index I. And then you can actually query, you need to be able to know like the set of all of the operators. You can actually, if you assume that the kind of DC component, as it's called, direct current component in signal processing, or like the 0th frequency of the kernel function at each order is 1, then you can query the index set of all the operators just by feeding in the constant signal, which is kind of a nice convenience. And so now, let me give you this definition. So morphism of Voltaire, a Voltaire series is comprised of first a function on the index sets. So for each operator in the source series, choose one in the target. Then for each such pair, give a map in the same direction between the domains of their kernels, of their kernel functions. And you need well, this is not as necessary as the other components of the definition, but I'm including this weight function for a reason I'll give in a moment. But basically from this data, you then get something I'm calling the weighted pullback, which is just so, yeah, you pull back the kernel function of the target operator for each one of these pairs, and then you weight it by the mask function. And from this data, we can obtain component morphisms indexed by the operators of S prime of R. And basically the way it acts is just that you for each operator, you pull back the kernel function of the one that you sent it to, of its match. And then you just multiply them, you act as normal, except you also now multiply by the tensor power of the product of the tensor power of input signal at order j, or sorry, order bracket I, with the kernel function at that same order, and now you multiply. So you're kind of causing the two systems to interact by multiplying the kernel function of the one with the fallback of the kernel function of the other. And so we can ask if this is natural, and basically it follows on the nose because we can commute so here's like the lower path, here's the upper path, and we can commute the order of these because they're all just of convolution type. Well, as long as you choose this weight function thing to be a convoluter in the time domain, you couldn't choose it to be a multiplication because multiplication and convolution don't in general commute. And there's a further technical restriction actually that I think I need to impose, which is that this math that you pull back along needs to preserve kind of these composite frequencies. So the two systems intuitively maybe need to like interact with the same set of frequencies. And I think this is essentially equivalent to you restrict the kind of the freedom to define this math is restricted to kind of the orthogonal hyperplanes that I mentioned earlier. So you can only send elements of those hyperplanes to other elements of the same. And yeah, that's in order for the map best, the component map to be well defined. And it's actually for the same reason, the same caveat I mentioned earlier, that you can't be sending frequencies in the input to images that like don't exist in the output. I don't know how better to say that, but anyway, so then we obtain a category where the objects are Volterra series and the morphisms are these natural transformations, which I should have mentioned earlier also have this kind of like lens type flavor. So they have the map on index sets and then the maps back for each such pair. And just as some examples of kind of Volterra series morphisms, if you choose all of the maps, kind of the data in the data of a morphism that I gave you to be the identities, you actually don't get the identity morphism. You get what you might call the autoconvolution. If you want the reason that I included this mask function is so that we have identities. You need to take basically the mask as the inverse of the spectrum. Because if you multiply with the kernel function by itself, you're essentially, if you convolve it by itself, rather you're squaring its spectrum. You used to be able to invert by that or normalize that. So and then translation I've included here because it's an example of what you might call a parameterized morphism. So I'm not going to go through it too much, but you can kind of translate by a different amount in each dimension by choosing the kernel function there to be a delta function that's shifted by some amount, and you can vary these shifts, and you can do so continuously, and this will generate index kind of index families of morphisms and so of Volterra series and so of outputs and so on. So I don't have that much time left, but I kind of
4 minutes.
4 minutes. Okay, so apropos of the theme, I should like to tell you at least a little bit about this. So there are these operations that have been defined that are well known in the Volterra series literature for how you can interconnect Volterra series, and in particular how you can sum, multiply, and compose them in series, and compose them in series. And just to kind of flash you some of the definitions, the sum is just level-wise addition of the operators and of their kernel functions. And so if their kernel functions doesn't change, and these are all basically what you would expect from the analogous to the case for polynomials. And so you can ask if it satisfies the universal property of the corresponding operations. And for the Cartesian product, and you can show that it does. I didn't introduce like sums in the base categories, which you would need, but for the Cartesian product, you can do the same. You get this, the order of nonlinearity of the resulting series is the sum then of the max of the orders of the factors. This is kind of, you can see a kind of binomial structure coming out for that. And most interestingly, there's the series composition, and this has, this can kind of write it out like this. These are not like formal string diagrams, I should say. And you can prove that it's associative. And I just did this by brute force in a way, by you can count the numbers of boxes of different colors and show that they are equal. So, okay, I have to end, but let me just say that there's this nice field called time frequency analysis, and it's somehow like inherently bilinear or quadratic, and it has nice applications to some of the early kind of operators in it were defined in quantum mechanics. There's a nice application to symplectic geometry, and Voltaire and the core operators in time frequency analysis can be represented as Voltaire series. So there's this thing called the Wigner-Ville distribution in particular that is used in time frequency analysis, and you can define it as you can represent it as a Voltaire series, and actually a more general class that are obtained of transforms that are obtained from the Wigner-Ville distribution. But you need a multivariate and parameterized Voltaire series, which are not too hard to do. And you get this form. So in particular, it has Voltaire series representation of the WVD as this form. It's like a product of this complex exponential and delta function. And that's it. So maybe just lastly, I'll say that there are some S2 extensions. You can define Voltaire series over other types of spaces, such as graphs and simplicial complexes. And yeah, that's it. Thanks very much.
Thank you. Time for questions, because we have time for 2 quick questions. Daniel.
So Volt of the monoidal structure.
Yes.
Yeah.
Yeah.
Tell us about that.
Yeah, well, so these monoidal, so I'm sorry I kind of ran through it, but not this one, sorry.
What's the definitional object then?
Basically, I mean, these operations are monoidal products on Volt. So yeah. Okay, so I mean,
so it's categorical, sorry, so it's categorical product and co-product.
Yeah, exactly. I mean, that's what I went through in the paper. I think it could be made a little bit more rigorous, but they should line up.
So there's no interesting non-universal product, like having a vector space is the interesting product, it's not a universal product, right?
Yeah. Yeah, the series composition is what I took as the kind of tensor product.
That's a non-universal.
Yeah, that's right.
Yeah.
Yeah. But the product, the Cartesian product and the co-product should line up with the universe, with the categorical
Just we
construction.
discussed over lunch, there's lovely lunch of stuff. I thank the speaker again, thank you. Okay, so last speaker of this series is Morgan Rogers from Laboratoire d'Informatique de Pavillon. How's my French? And the title is Building Models from Finite Pixels.
Thanks very much. Thanks for accepting my talk, and thanks for placing me in a session where I can give you all some whiplash from Fourier analysis to logic. We'll see how that goes. Now, interestingly, I'm having the same problem as earlier. This is supposed to be orange, but it's mostly black. So I promise you there is color in my slides, you just won't be able to see it. So this is secretly actually somewhat introductory talk to topos theory. So I'm going to tell you about 3 different ways of building or presenting toposes. And the remaining 2 parts of the talk are going to show you how those parts interact. I should note in particular that the models in my title are models in the sense of model theory. So we have some fragment of logic, some formal theories that we can use to describe objects that we manipulate in maths. I'm going to tell you specifically what part of logic I use in a moment. And the models that I'm talking about are models of those theories, which is to say interpretations of the ingredients which validate certain formal axioms. So as you may know, if you've heard anything about topos theory, there are the big reference text is called Sketches of an Elephant, so I've included some of those. The first perspective I want to give you on toposes is as they relate to theories in a fragment of logic called geometric logic. Now, to describe when I talk about fragments of logic, what I mean is we can construct formulas starting from some basic ingredients. So maybe I give you a base sort, I give you some operations. These form the signature sigma. And then I can use those to construct, for example, equations or basic terms that express relationships between things constructed in that language. And the fragment of logic describes what connectives I'm allowed to use to combine those. So in geometric logic, I'm allowed to take disjunctions of arbitrary size, indexed by a set. I can take only finite conjunctions, and I can take existential quantification. So the point is that what's not in that list, so I can't universally quantify. I don't have implication or negation native to this logic. But when I talk about theories, so my axioms will be presented like this, that can be thought of as implications between different formulas built in this language. I'll explain later how that actually turned out to be constraining in the construction of this talk. But generally speaking, this is a very expressive fragment of logic. In particular, it includes a significant portion of finitary first-order logic. So everything in universal algebra and some variations thereof can be expressed in this logic. So what does it mean if I have a category, what does it mean to take a model of one of these theories in that category? Well, I start with this signature. So I have the language, which consists of some sorts and some operations, and those become objects of my category and morphisms in my category. And in order to satisfy an axiom, I need to be able already to interpret the formulas in terms of those basic interpretations. But as soon as I can do that, satisfying an axiom is just saying that one sub-object interpreting a formula is contained in another sub-object interpreting a formula. Hopefully I'll get to some examples of that later, but the important part for us is how this relates to toposes. So I'm not going to tell you what a topos is in this talk. Even more than usual when I give a talk, I usually say I'm not going to tell you what a topos is, but I'm going to give you no details of the internal structure of one of these things, except that it's a category with certain properties. And so it makes sense to talk about functors between those and in particular adjunctions. So a geometric morphism is the type of transformation that we typically consider between toposes. And it consists of an adjunction where the left adjoint, the upper one, F upper star, is required to preserve finite limits. So secretly, what's important about that from the perspective of this logic is the interpretations of each of these connectives is preserved in terms of the corresponding categorical structure by these left adjoint functors. And what that leads to is a representability result. So if I give you a theory, firstly, if I take any topos, it has sufficient structure that I can talk about models of that theory inside the topos. But moreover, I can build a special topos related to the theory, which is called the classifying topos, such that geometric morphisms into this classifying topos correspond to models of my theory in that topos. So actually, for the rest of the talk, we're not going to need to consider general E here. We're really only going to be considering the case where E is the category of sets. So what this says is, for any geometric theory T, I can construct some topos set square brackets T. So the reason I use this notation is because we think of this as adding freely a model of my theory to sets. Such that morphisms from the category of sets into set T are going to correspond to models of my theory in sets. Okay, that's one perspective. Here's another way of building toposes. And this one's much more algebraic. So suppose I give you a topological monoid. Again, maybe some more whiplash from Fourier analysis to logic to actions of monoids. But I can remind you what an action of a monoid in general is. It's a map that looks like this. So I'm going to call my monoids L in this talk because I'm reserving M for models. So if L comes with a topology, I can still let it act on sets in a continuous way by just thinking of sets as discrete spaces. So this imposes a non-trivial condition, but the reason I want to stick with acting on sets is because that keeps me in the world of toposes. So firstly, I'm just going to tell you this gives is another way of constructing examples of toposes. One thing to note is that this continuity condition, because I'm making the sets discrete, if I have any big connected components in my topological monoid, then those will be completely crushed or ignored by this construction. So if I take the real numbers with addition, for example, and I get them to act continuously on sets, they can't do anything interesting because they can't move the points around due to the continuity, meaning that I would have to be able to get from 0 to anywhere else. So for that reason, I include some examples. If I just take an ordinary monoid where the topology is discrete, then we get what you'd expect. But particularly, well, examples where the topology is non-trivial include profinite things and prodiscrete things, which you may or may not have encountered before. But these include in particular if I take function spaces. So say I take the natural numbers and I look at endomorphisms of those, not with the discrete topology, but with the topology that where the open sets are determined by values at individual points. Okay, so these are the two that are going to be crucial for expressing the questions that I want to answer. First of all, I've talked about geometric morphisms from set to E, and implicit in this construction from the previous slide is that if I have an action of my monoid on a set X, I can just forget the action, and that gives me a forgetful functor from this category of continuous actions to the category of sets, which turns out to be part of a geometric morphism. So if I have a topos of this form, then it comes equipped with a special point where the left adjoint is the forgetful functor. And actually something much stronger is true, which is that if I take any topos and I equip it with a point, then I can look at the endomorphisms of that point. So these will be natural endomorphisms of the functors involved, either the left or the right adjoint. And that comes equipped with a natural topology. And that gives me a co-reflection from arbitrary pointed toposes to these toposes of monoid actions. So that's great. I mean, I've not just told you about a class, but I've told you about a class of toposes that's special in this way, all without telling you what a topos is. But this doesn't really tell me anything about the logical perspective. So I told you that any topos, or in fact, I didn't say it out loud. There's a converse to this theorem from earlier, which is that any topos classifies some theory. And so what this talk is seeking to address is, when do we have a relationship between these two presentations of a topos? That is, if I'm given a monoid, what types of theory does it classify? If I give you a theory, can I tell that the corresponding classifying topos is the actions of some monoid? And we've already seen something that has to be special about the theory, which is the existence of this particular point from which I can recover the monoid. So this must be a model of that theory, and it has a bunch of particular properties. So another way of asking this is, if I show you a theory, can you tell whether it has a model with nice enough properties? Okay. In order to answer that question, in order to even start answering it, I'm going to show you yet a third way of constructing toposes. And before I introduce it, the first way in terms of logic, because of the converse of the theorem, that was completely general. Any topos has a corresponding theory. The second one was not. There are particular further properties when I know that my topos is of the form continuous actions of some monoid. So this third way is going to be, again, a completely general presentation. And that is in terms of sites. So the usual definition that's given of Grothendieck toposes, which, because I won't give it in full, still won't tell you what a topos is the category of sheaves on some site. So pre-sheaves you may have met. They're contravariant functors from my given small category to category of sets. This J, or the Grothendieck coverage or Grothendieck topology, is extra data that I can associate to my category. And I can derive from that data conditions on pre-sheaves, and the objects which satisfy those conditions are called sheaves. So I can take this full subcategory on the object satisfying that extra condition. And it turns out that not only do we construct a full subcategory this way, but it's reflective and the left adjoint preserves finite limits. So this gives another instance of a geometric morphism. Okay. So it's much easier to associate this presentation of a topos to our continuous actions. Essentially, the canonical one, although there are many, is to look at the principal actions. So that is, I fix my monoid L, and I look at the continuous actions which are generated by a single one of their elements. So if the topology on my monoid was discrete, this would just be all of the quotients of my monoid acting on itself in the category of actions. But when the topology is not discrete, that action on itself doesn't actually live in the topos, but it's still conceptually useful to think of it that way. These are somehow all of the quotients of my monoid, which identify enough stuff to make the action of L on itself continuous. Okay. Then I need to tell you what the Grothendieck coverage is. And to tell you in general what a coverage looks like might be complicated, but here my task is simplified by the fact that the data is generated by individual maps. So essentially the things which cover are just, I take any principal action and I quotient it. The quotient map is required to be covering in the sense of belonging to this extra data of the coverage. Okay. Why do I need to pass through this third way of presenting toposes? It's because if I can compare my category of actions to a pre-sheaf topos, I have a much more direct way to understand what kinds of theory will show up. So rather than giving syntactic constraints on my theory, rather than saying, here are a bunch of conditions on what kinds of formula can appear in my theory, really what this is going to constrain is, what do the small models of my theory look like? So if I know that I have a classifying topos for some theory that's equivalent to pre-sheaves on C, then I can extract the finitely presentable models of T. So actually, very concretely, those are the models which are presented by a finite number of generators and a finite number of relations, all in the language underlying T. So this FP can be interpreted very concretely on the syntax side, or categorically in terms of some interaction with colimits. And I have a guarantee that that category of finitely presentable models is going to be equivalent to the opposite of my category. So again, this doesn't necessarily tell me anything syntactic about T, but if I give you a theory and you're able to figure out what the category of finitely presentable models looks like, then we have some grasp on when that could be the kind of category that we're looking for. So I've introduced K here as notation for the finitely presentable models. I'm going to keep using that, but that makes this line of the board fairly confusing to look at. The thing I want to emphasize here is the relationship between these finitely presentable models and the category of all models is that the latter is obtained by closing under filtered colimits. So I can take any model and think of it as a colimit of all of these finitely presented ones. How am I doing for time?
You've got,
Okay, great.
actually 12, sorry.
Okay. So that's for the pre-sheaf case, but of course, we're not looking at the pre-sheaf case, we're looking at a subtopos. We're adding this data of the coverage. And so the thing to know to join all these loose ends together is that when I take a subtopos, when I add this coverage, it corresponds to adding axioms related to that coverage. So it's possible to make that precise. I probably won't before the end, except in more concrete examples. But the idea is, rather than looking directly for my theory T, I'm going to look for some theory which is of pre-sheaf type. So where I can just look at the finitely presentable models, and then I'm going to try and identify when I can reconstruct the subtopos of the right form. Okay. Maybe I'll just say that again in a different way. I think this if should not be here. So my continuous actions of my topological monoid will classify a quotient of any theory T. Again, there might be several theories with the same category of finitely presentable models, as long as that theory is of pre-sheaf type, and the category of finitely presentable models is equivalent to the opposite of my category of principal actions. Okay. So, fine. So far so good. Actually, I'm transitioning between parts. I've given you the three perspectives on toposes that I'm going to use. And now we're really going to go straight from this corollary to figuring out what the constraints on this category of finitely presentable models have to be. So the first is that there's an orthogonal factorization system. So if I take my principal actions, I'm still considering all of the morphisms between them, but there's a very natural epi-mono factorization, just surjection, injection factorization on the morphisms, and that dualizes nicely, so that's going to be inherited by K. More interesting, or maybe closer to the model theory that behind the scenes is motivating all of this work, are what's called the joint embedding property and the transferability property. So the joint embedding property says, if I take any two finitely presentable models, I can find a bigger model into which they both embed. Fine, that's a fairly well-named property. The transferability property says, if I have an embedding of one model into a bigger one, and I have any morphism to another finitely presentable model, then I can close the square such that, using the notation here, Z will embed into a larger W from which emits a morphism from Y, closing the square. So compared with more classical model theory, the one that appears in the classical version of the story, where monoids would be replaced with groups, is the amalgamation property, which I'll draw both for comparison. So here I'm asking for just one pair of opposite sides to be mono. And here, for the amalgamation property, I would be asking when X embeds into two different ones, then those have a joint embedding. Okay, I would like to hurry up, but the conditions are many and fairly important for the main results. So a theorem that's implicit here that I won't go into the details of is this orthogonal factorization system on K extends by just taking colimits to an orthogonal factorization system on the full category of models. So I can use those to express what the actual properties of a special model should be. I told you it was special. I didn't tell you how it was special because I didn't yet have the language to describe it. So here, X and Y live in my category of finitely presentable models, and M is going to be something more special. So I ask that whenever I have a morphism from a finitely presentable thing and an embedding, then I can extend along that embedding. So I can always find a copy of Y in M whenever I have a copy of it. The second property is that everything has to embed into M. And the third is that I can construct M as a colimit of these embeddings, so things in the right class of my factorization system. Okay. So this tells me how M has to be built and the relationship it has to have with finitely presentable things. And crucially, these are not just necessary conditions, they are also sufficient. This is really exactly what I'm looking for to have the right properties to answer the question. So unfortunately, the conditions I identified in the previous slide are not quite sufficient on their own. I need some extra assumption on either the size of the category or on the ways that I'm allowed to put things together. The simplest instance of this is just to constrain the size of the category of models. So when I say it's countable, I mean there has to be countably many morphisms in total, or at least there is an essential subcategory, an equivalent category where that's the case. So I included a proof. I think all I want to stress is that it's by induction. And I want to show you on the next slide where I actually use the properties from earlier. So I'm using induction to construct these finitely presentable models UK. And I'm going to take the colimit of a big diagram of those to construct the model I'm looking for. So to do that, I enumerate all of the things I'm required to be injected with respect to, and I use here the transferability property and here the joint embedding property. So in each induction step, I need to use both one after the other. And the end result is that the colimit of all of these will have the properties that I'm looking for. Fine, so there's some probability that at least one person will be familiar with Freisey limits or the model theory background that this is based on. So classically, if we just had the amalgamation property and we asked that all of the morphisms that we were considering were embeddings, we would recover the classical Freisey construction. Thanks. Okay. So just to summarize, I've given you necessary and at least one sufficient condition on a theory T, such that there is an extension of that theory T, which is equivalent to the topos that we were looking for. And that doesn't sound like it quite answers the question, but the crucial thing here is typically this quotient, this extension T primed, it is very far from being of presheaf type, in the sense that we have none of the finitely presentable things from T actually live in T primed. So the reason or a justification for having to do things this way is it gives us the small part decomposition that we need to actually reconstruct the model that we're looking for. All of this has been very abstract, and so I would like to give you some examples. And it's a lot easier to give examples in the classical case of the SYCO construction. So if we consider the rational numbers with just their order structure, these can be constructed in this way as a co-limit of finite pieces for the theory of dense linear orderings. That is, where between any two elements, I can find a further element. And I don't know to what extent you'll be familiar with any of these examples. The idea is always, whenever I have an infinite thing that is naturally the limit of all of its finitely definable pieces, then it's typically going to be an instance of a construction like this. Okay, now I don't have time to present the thing that kept me up last night, but that's probably for the best. I'll just give a quick description of it. It's a theory completely unrelated to the ones before, Boolean algebras with an action of my particular monoid L. So I'm cheating a little bit. The monoid is already involved. And really what I'm showing you is a way to build a theory directly from a monoid. And then I add some further conditions which impose finiteness on the finitely presentable models, and which force the models to be connected in a sensible way, which, if correct, I don't expect you to be able to check this at short notice. These extra axioms are designed so that the finitely presentable models are exactly the finite Boolean algebras equipped with an action of M, and moreover, those which are dual to the finite principal left L sets. So exactly dual to the category from earlier. Blah, 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 blah. The reason that this kept me up is because it turns out if I have a theory where the finitely presentable models are closed under products, then this implies this. And so I can always reduce to the classical story by just ignoring any morphisms that aren't embedding. So I needed to come up with this fairly contrived example where I don't have products in order to give you an example that doesn't reduce to the kind of group theoretic case. That's it. Thanks very much. Yeah.
I'm just a bit, it's probably quite a naive question, but what's so special about monoids or topological monoids that, like most bases?
I wouldn't say it's something that's particularly special about them inherently. This is based on work from my thesis, which was all about exactly that type of topos. So topos is constructed in that way. And the motivation for me was that people seem to have done loads and loads of studying of groups, but there was no reason that couldn't extend to monoids. And so I wanted to see what the consequences were, like how far that extended from the perspective of logic, or from the various other ways that you can look at these topos.
You need to have a topological.
Oh, I see. Well, you can just run the story with discrete monoids, I guess. So this just gives a broader class, but in particular, this theory I say on this slide in gray, the topology on the group, like topological groups, are really needed for these classical examples. So in particular, it's important that the endomorphisms of this monoid are given a topology that is almost always non-trivial.
Any other question?
There's an online one. The question online.
No question online.
So
Do you want me?
yeah, well, maybe there's a specialized question, but can you say anything special when the monoid question are inverse?
Yes, but not in this short amount of time. I mean, I'd have to figure it out. I haven't thought about it extensively. Already, this example that I gave at the end is the first time I've managed to find one that was built from or explicitly described logically for a non-trivial monoid. So I haven't thought about further restrictions of that yet.
Maybe we can give you the name of the person who's asking.
Yeah.
Peter Hyman, sorry.
Yeah, okay.
Yeah.
Thanks.
Okay. Okay, and one
Well,
more.
my follow-up was kind of my question was kind of a follow-up to the first question. Is there something where you get, for example, if you have your topological monoid act on non-discrete spaces, or maybe if you take localic monoids or something?
So yes, definitely. And in particular, that's something that there's a lot of motivation to do because there's plenty of topological monoids that people are interested in that, you know, don't act nicely on discrete spaces or interestingly. But the personal obstacle to that is that you immediately get out of the realm of toposes. And so, you know, trying to extend this logical story, I wouldn't necessarily know how to do. Obviously, you can restrict to a class of spaces where some of it might transfer, but well, I can go into some subtleties over lunch, but that's the basic answer.
Thank you again. Thank you. Lunch, like before, it's on the third floor.
Oh, yeah. As long as we have enough.
No, that's interesting, but recent work by that is people at Talent have has explored index containers or monadic index containers. They haven't looked at distributive laws over them yet. So yeah, that's another direction that we could extend this work into. But I think index containers, they kind of there's some way in which they're subsumed by just normal containers anyway. So it's yeah, for us, it feels a bit more interesting to go down the sort of groupoid route where we're imposing extra structure on the set of shapes. Yeah.
Okay, thanks very much, Chris. I know there are more questions, but in the interest of time, I think we'll move on. Let's thank Chris again. Okay, Alessandro, over to you. Take diagrams from the monoidal monads.
Thank you. So this is joint work with Filippo Bonchi, Giuliano Pinacciocco, and Elena Di Lavore. The talk is going to be about diagrammatic languages, especially tape diagrams. So now you may be familiar with string diagrams, but maybe not with tape diagrams. So I'm just going to start by saying what they are. So very informally, they are string diagrams of string diagrams. You can think of them as string diagrams where the wires are tapes, indeed, ribbons, so thickened wires. And inside of these tapes, there are traditional string diagrams, so boxes and wires. This sort of hierarchical structure highlights the fact that there are two monoidal products happening. One is, let's say, a multiplicative one inside of the tapes. So, for example, this of this and D is in tensor, this tensor with the identity inside of the tape. While, for example, this tape here is in plus with this tape. Tapes can cross, you can compose them sequentially, there are identities, there are also these branching of tapes, let's say branching and merging, and these, as we will see, impose some restriction on the outer monoidal product. So more formally, tape diagrams are a universal language for Rick categories with finite byproducts. A Rick category is indeed a category with two monoidal structure, one distributing over the other, witnessed by these natural isomorphisms. Moreover, we ask that the class is the byproduct. And then there are many coherence conditions favored by Laplace, coherence for distributivity. So what does it mean that it's a universal language? Well, in the very same way, string diagrams are a universal language for symmetric monoidal categories. So one way to formally present them is presenting them as a term language. The tapes are formed with these two layers grammar. The first layer is generating string diagrams, traditional string diagrams. While the second layer, the tapes, and especially this third production here is what is saying that the string diagrams generated by the first layer are embedded inside a tape. Again, remember that we have this additional structure, which is the branching or copy, discard, and co-copy and co-discard of tapes. The two layers are the terms generated by the two layers are both quotient by the absence of symmetric monoidal categories, and moreover, we ask that these additional structures form commutative monoids, and moreover, they are components of natural transformations. All in all, by Fox's theorem, this means that the monoidal product of tapes is actually the byproduct.
What is sesquistrip?
Yeah. So basically, sesquistrip means that the two monoidal structure are strict, and then only one of the two distributor is the identity.
One of the two, okay.
Otherwise, everything would.
Are you gonna tell us which one or?
You can choose. You can choose. We chose for the right one to be that. Yeah, in the paper by the plaza, you will see them called the right street or left street. Okay. Yes. Yes, yes. This is all in the original paper. Okay, so some examples of the things that you can do. So, for example, take your favorite string diagrammatic language for expressing quantum processes. This would be the ZX calculus, or simply something that lets you represent unitary matrices and scalars. These take semantics in finite dimensional Hilbert spaces, which happen to be a finite byproduct Lie category with two tensor products, and so you can embed them inside tapes and form, for example, a controlled unitary in this way, where the branching and merging lets you explicitly represent the control part. So in a recent paper, again, now we extended this thing with traces for the outer monoid product. And this allows you to represent imperative programs. So for example, this tape here is representing this while program. And this can be interpreted again in a finite byproduct category, actually more because you have the trace. Which is real with the Cartesian product as the internal, well, the multiplicative monoid product and disjoint union, the disjunctive one. So we may wonder if there are more examples for example, probabilistic behaviors. And take, for example, as a semantic universe, the clarity category of the subdistribution monads, or simply if you want substochastic matrices. But this doesn't work quite well. I mean, we cannot use the language we have so far, and you can even see it diagrammatically. Now we don't have the branching of tapes, but we rather have this thing that is parameterized by the probability that probability branching. So in particular, in this clarity category, the outer monoid product is only a coproduct and not a finite, sorry, a byproduct. And moreover, there are these additional operations like the probabilistic branch. So what we would like to do is to, I mean, we take this probability example as a leading example and try to understand what are the structures and property placed in this pure category, and define a suitable notion of a Lie category and diagrammatic language for it. So let's take a closer look. We already saw this yesterday, I think a couple of times. Well, I just quickly recall that I'm taking the subdistribution monad on sets. So objects are sets. Morphisms are functions that map elements in X to a subdistribution over Y, and composition is summing over the middle variable. There are two monoidal structures at play. Here on objects is the different product, while here is the joint union, and on our side defined this way. But interestingly enough, you have internal commutative comonoids for the multiplicative part, and internal and natural commutative monoids for the disjunctive part. And moreover, there are some interesting arrows. This is the one we saw before in the diagram, which basically maps an element in X to this distribution, which is the one assigned probability P to the first branch, and probably 1 P to the second branch of the probabilistic branch in the result before. And then the star mapping an element into the null subdistributions. Now, all of these may seem arbitrary, but actually the fact that we have a copy discard category and finite coproduct category, so another monoids, happens for any symmetric monad, well, on set, but actually on any finite coproduct category. And moreover, we have this kind of additional structure when the monad is presented by an algebraic theory. In this case, is the pointed convex algebras. Now, I'm not listing all of the axioms, only the two operations, but these are pretty standard. So from this, we build, let's say, abstract away from this example, and we build a notion of Rig categories that we call finite coproduct copy discard Rig category, where we require indeed that the multiplicative part is a copy discard category, and the disjunctive part is a finite coproduct category. So these are I mean, components of the Navier transformations. And the monoids and comonoids interact via these coherence conditions. So one of the results that we have is that if C is a finite coproduct copy discard Rig category and T a symmetric monoidal monad, then the classic category over P is again a finite coproduct copy discard Rig category. Now remember that in subdistributions, we also had this additional, let's say, algebraic operation. So on top of the definition we just saw, we want to add these algebraic operations. And so consider an algebraic theory given by a set of operation generators and equations. Then a TCD Rig category is what we just saw, finite coproduct copy discard Rig category, together with a morphism of a functor of finite coproduct categories that go from the opposite of the Lovier theory associated to the algebraic structure to C. And it is all such that this diagram here commutes, where RF0 is the free finite coproduct category on a single object. Well, this is all the technicalities, but the important thing is that this implies that for every issue can be sigma, but actually for any term in the of the algebraic theory from n to 1, there is another transformation built in this way, using the morphism I in the definition and the distributor and annihilator of the Rig category. So this definition brings us to a diagrammatic presentation of what we just saw in terms of tapes, which are an adaptation of the original ones. In particular, now in the first layer, we want the copy discard structure. So we add indeed the copy and discard for the string diagrams. While in the second layer, we dropped the branching of tapes because we don't need it. We don't want it anymore to be a byproduct, the mono product. But we had some representation for the algebraic operations in T. Again, we portion everything by the axiom of symmetric monoidal categories for both layers, and then we ask those for copy discard, the products, the fact that the algebraic operation is an another transformation, and then, of course, the equations in the algebraic theory. So then, one of the results is that these T tapes are the free circumscript TCD category generated by a monoidal signature. And what this implies is that if we have a category of string diagrams that we can interpret in this TCD rig, in a TCD rig category, you know, semantic category that exhibits these structures, then this semantic factor extends uniquely to one that goes in from the tape diagrams where the string diagrams have been embedded into to the semantic category. More or less like we saw at the start with the examples. Quantum string diagrams can be interpreted in finite dimensional vector spaces and which are a finite byproduct category, and then building the tapes on top of it is allowed, let's say. So let's go back to the probabilistic example. So consider now indeed a language of string diagrams which are the Boolean circuits. So we have and, or, negation, 0 and 1, and also the quality check. This can be interpreted in this classic category to observe that there is no probabilistic behavior here. We add it on top by embedding them inside tapes over the algebraic theory of pointer convex algebras. And so one can, for example, form the coin flip by taking this diagram, which selects 1, 0 with the probability P or 1 minus P respectively. So now in this language, there are two ways of doing probabilistic control. One uses purely the multiplicative part and is multiplex, and that has been exploited in this paper by a bunch of people here at UCL, where they managed to prove completeness for substochastic matrices with respect to the times. And one is given by the additional additive structure, which is instead really a convex sum. So a few words about the multiplexer. This works. So in this example, if you plug a P on top and two circuits CD on the other two wires, then you will select the output will match the one of C, the probability P, and the one of D, probability 1 minus P. Here, the behavior is the same, except for one case, when one of the two circuits is the null, so this is when is a failure. So, for example, when you check that 0 is equal to 1. In this case, in the multiplicative case, since you are multiplying failure, this behavior propagates, and so if any of these two is a failure, then the whole diagram will be failure. And you can also think of it like an if then else, which evaluates both branches without knowing about the count. While in the convex sum, this doesn't happen because there is this disjunctive behavior, unless both C and D are failure. Okay, some future work. Possibly we would like to give a complete axiomatization for this rig category, maybe exploiting existing completeness theorems, like the one that I quoted before, and then maybe add traces on top of the language with probabilities. And this following up the work we have without probabilities would give us a probabilistic and diagrammatic program logic. And of course, the leading example is classically of the class distribution, but we would like to look also for other examples. Yeah, that's it. Thank you.
Questions? Yeah. So first, like when you're doing diagrams for circuits, a nice thing is that you're close to how engineers think about circuits, how they develop that in practice. Let's say, is there anything analogous for tape diagrams? Does this correspond to anything that they do already?
So,
and the other one is when you do this comparison with your approach and our approach.
yes.
Does it correspond to anything control, like it was about
So I'll answer to the first
Yes.
question. So something that came to my mind, especially in this case, where also we have traces and they're expressed in programs. So in computer science, you usually have, even in compilers, you have these data flow and control flow graphs expressing indeed the data flow and control flow of information. One way of thinking about these kind of tapes is a mix of both, where the data flow is happening inside and the control flow outside. I mean, the branching and the tracing is what is give you the control, while again the copy discard structure inside the tapes is how the data flow. I mean, like how you share resources and these kind of things. So yeah, there is an analogy. This is the best one, you know. About the combinatorial interpretation, not that I know. Well, I really think about it.
Just because when you compare these two constructs, one to think of one to have a lower level of the other. So like a way we implement it. Now obviously one is more general than the other, but still it looks like the more.
Yeah. Yeah, I don't know, it's interesting to think about it, but the way I see it is that here you are kind of emulating disjunctive behavior, while here you really one. There are nuances also here because, I mean, this one is a translation only of this diagram here. So we don't have a general multiplexer with an open Y for a graph, right? We always have the bench that is parameterized. In the disjunctive case, yes. I mean, the interior you can see it. But yeah, I mean, it's a good point. It's not it's such a comparison that you could just.
Do we have a question online? I noticed that
Yes,
there's something.
we do have a question online, so the line is saying, you mentioned Laplace's 1971 coherence theorem at the beginning. However, you consider distributivity to be mediated by isomorphisms, whereas you consider some monomorphisms. Is there anything gained, lost in the more general case?
I didn't get the question. So can I even see it from
You can read on there.
I don't really have an answer for that. Well, yeah. Yeah, I'm not sure. I should look into it better before answering. Sorry.
Okay.
Yeah, I'll check and
That's okay.
get back.
Thanks, Peter. You've defeated the speaker. Any more questions? I think there was another question that I saw. Yeah.
Yeah, I want to know if there's like a direct connection with distributive Markov category.
Yes. But I need that is another category, no?
Yeah, I think in distributed, you assume that the distributors are the canonical one and the product. But I mean, it's just.
Okay. The only thing that I'm against here is the naming. I would prefer a better naming. Then what is a free co-product copy discard free category like. Yeah, exactly. Distributed copy discard.
Yeah, but distributed, you usually assume that the distributor is.
Okay.
Which you can always.
Okay.
Yeah.
Okay, is there another question? Yeah.
How about tape diagrams related to sheets?
Sheet diagrams are more general because you don't have to require the byproduct, but requiring the byproduct lets you be in 2 dimensions rather than 3 dimensions. Buttons.
Okay, so let's go on to the last talk. Thanks very much, Alessandro.
Did somebody take the cable? Uh-oh. Oh, it's being plugged into itself. Good. Nice. Let me do this. Stop extending. Is this got 2 screens? Oh, it does have 2 screens. Okay, let me. That's fine. Okay, and then you want me to share screen? Wait to send me to you. Yeah. Thing in the edge. Thanks. Great.
Great. Okay, so for our last talk today, we have Nick, who's telling us about this nice collaboration, SD Visualizer. Let's break tradition by starting with applause because Nick passed his PhD vibe last week.
Thanks to Jamie's great supervision. Well, I'm very happy to be here. I'm going to talk about SD Visualizer. The SD stands for string diagram. No surprise to anyone. This is joint work with Alex Rice, Callan Tataru, and Dan Geeker. This is work that we did when we all did an internship together in Huawei Programming Languages Research Lab, which Dan runs up in Edinburgh. So yeah, let me tell you about it. It's going to be sort of a bit of a wild ride, linking programming languages, applications, and category theory and string diagrams. Okay, so not going to really assume anybody knows anything about programming. So I'll start from the top. What's a program? It's generally some sort of sequence of instructions that will compute something. And a sort of very toy example of that would be something like arithmetic. If I have this expression on the left, which is going to be some sum, then we can see that as like a computation, which can be done sort of step by step to produce a final value, which is just some integer 28. And we can think of this equality as, instead of being a symmetric thing, as like a directed thing, because your computer will sort of simplify this down as it computes. In some sense, that is what we think of as computation. But when we're working with actual computers, of course, they don't understand the theory of arithmetic in this way. What they do understand is something like ARM assembly machine code. So there are programs that we use to turn these kind of high-level platonic ideas of what we want our programs to do into a sequence of instructions which our machines can crack the handle. And those programs are called compilers. So a compiler would take this sort of thing, and it would generate this sort of thing. And that's going to be like a non-unique process. And many people work on just the art of constructing a compiler, making sure that it's good for some sort of some definition of good, whether that means it's really correct, or it produces really fast code, or it runs really quickly, or it's easy to maintain. There are many different sort of software engineering concerns. Okay. So compiler optimization then is going to be encoding some sort of extra rules in our compiler, which will allow us to sort of leverage the theories that we care about. So we know stuff about the theory of arithmetic, and that if you add the same number to itself 4 times, that's the same as doing a multiplication by 4. And in the machine world, when you are thinking about ARM assembly, it is more efficient to multiply something by 4 than it is to perform 4 addition operations. So an optimizing compiler would see this arithmetic expression, and it would see that it can replace this with something which is semantically equivalent, that being multiplying by 4. And then that would let you generate this shorter, more efficient program. So here I'm sort of measuring the speed of your program by just the number of instructions the result gives you, which is not entirely unreasonable. It's not entirely sound either, but it's a good first approximation. And that's sort of the game here. We want to, as sort of mathematicians and smart people who want to solve problems, we want to use like high-level abstractions and fancy programming languages, things like Haskell, but ultimately, at the end of the day, it needs to be sort of compiled down into something like this, which you don't really want to be writing by hand. And you absolutely need compiler optimizations in order to be able to produce code that is fast. Sometimes you do sort of have to go into this world a bit more when you're actually programming, because every sort of second matters, but the sort of dream would be to make it so that you don't have to do that at all, and you can just let your compiler do all that work for you. And obviously we care about soundness of our compiler optimizations. It's no good if our compiler changes our expression to something which doesn't mean the same thing, because then, well, which just breaks the whole contract of everything. So in order to talk about what it means for compilers to preserve semantics, you need to talk about what it means for programs, what programs mean. And we can think of programs as sort of types in a type theory. And that can be as arithmetic expressions or as lambda calculus. And a particular form of that is what's called denotational semantics.
which is the idea that we can associate to programs certain mathematical objects. And categorical semantics is like an extension of this, which is using the language of category theory to do that. So it sort of builds on, historically, first there was maybe domain theory, which was about interpreting these kind of programs in different types of order theoretic structures like lattices with extra properties and stuff. And a particularly famous instance of this categorical semantic correspondence is called the Curry-Howard-Lambek correspondence, where you have that the simply typed lambda calculus is the internal language of Cartesian closed categories, which means that sort of all of the reasoning power that you have in the simply typed lambda calculus completely soundly and reflects the structure that you have available to you in a Cartesian closed category. Okay. And then if you think about what categories give you, well, they let you tell what categories are is like as an extension of sets, rather than letting you know if two sets are the same. You can express like an isomorphism between objects, but what you have is an equality operation in the Hom sets. So in order for programs to be the same thing, then we want to interpret them as morphisms, and then they will have the same meaning when that equality operation in the category says that they represent the same thing. And then getting really down to basics, what is a computer? It's just kind of a string processing machine that will take bits, zeros and ones, regions of memory, and then it will do some churning on it and then give you more zeros and ones. So the point I'm trying to get at is every program actually needs to be encoded into some sort of machine-friendly form. And you care about which one that you use because it affects the kind of data structures that you're going to use, the kind of optimizations that are going to be easy or hard to do. And the sort of traditional way that you might represent programs is as these kind of trees, these abstract syntax trees. And in this talk, I'm going to talk about how maybe you might want to use string diagrams instead. So maybe people haven't seen lambda calculus before, but the basic idea is you fix a set of an infinite set of variables, so you never run out, and then you inductively define the terms of the lambda calculus. And this is like a nice formal model to represent computation under sort of beta reduction, where the lambda is some sort of binder symbol, like a for all or an exists in propositional logic. Sorry, not propositional, in first order logic. So variables are either bound if they're under a lambda, or they're free with respect to some term. And this gives you a kind of structural equivalence called alpha equivalence, which is the idea that the sort of names that you picked for these bound variables under the lambda, they don't really matter. Now, yeah, so you'll see later on, but also before that, in the traditional representation of programs where you have an abstract syntax tree, that is not going to be an alpha invariant representation because you have these different names appearing, and that's a bit of an issue. So string diagrams, I don't have to belabor this too much, but they're like a term calculus for morphisms in different types of monoidal categories. And for instance, you might represent this term in a monoidal category like so. And they're really cool because you can turn the isotopies that you can imagine on this into the sort of structural ambient equalities that arise from the structure of the category in which you're working. And in a Cartesian setting, you have this nice copy delete structure, which we've seen lots in this meeting so far. So my string diagrams go top to bottom because data flows from top to bottom in sort of these kind of data flow crowds. So it's a bit of a, you have to flip everything upside down if you've been looking at the other talks. And you know, this idea has been used a lot in lots of different application domains, but not really that much in programming languages. So in order to store these string diagrams on a computer, we use the hypergraph formalism, which I guess a lot of people in the audience will be familiar with. Some of the people, the inventors are here, I guess. Fabio, and some other people. So it's based on this idea from string diagram rewrite theory, that you can encode this string diagram structure as something called a hypergraph. And a hypergraph is just like a directed graph, but you have, instead of an edge relation, which has a source and the target vertex, you have a generalization where you have sort of K ordered source vertices and L ordered target vertices. And then we say that a hypergraph is discrete if you only have vertices, no edges. And this is a little small, but this is a drawing of such a hypergraph. So here there is a hyperedge E3 with two source. It's got a first source V5 and a second source also V5. And this is another hyperedge. It's got three sources and two targets. But it doesn't look like a string diagram. So what we're going to do is we're going to sort of carve out some sort of substructure of this, which is going to represent string diagrams, at least in symmetric monodal categories, which is, I'm just going to explain this one because it's simpler. Here's an alternative definition. If you take tree sheaves over this category with pairs of natural numbers plus an additional object and a bunch of morphisms, that will give you the same data as what I had before. And this is really nice because tree sheaves are just really super well behaved. Having, as a consequence of this category, defining this category as a tree sheaf category, you get a bunch of stuff. It tells you what the homomorphisms of hypergraphs are. It tells you that you have all the co-limits because it's tree-sheaf topos. So that formalizes the idea that if you draw a hypergraph, you draw another hypergraph, you can sort of connect it together where it will meet, glue things together, which we care about with string diagrams because we build bigger string diagrams by juxtaposition. And it also lets you talk about hypergraphs with respect to some kind of signature arising from some sort of monoidal theory or something like that, which represents the algebraic theories in which we're working. So for instance, this might be a plus operation, which is arity 1, co-arity 2. Now, a hypergraph with an interface is defined to be it's a cospan between discrete hypergraphs. By taking cospans over that category before and then quotienting the morphisms, you don't have like a bicategorical structure, you just get a categorical structure. You think of the objects in the category as being sort of the boundaries along which you are able to vertically compose these string diagram-y hypergraph things. So like so. This we might say that this entire cospan is a hypergraph with an interface where the boundaries are discrete and they represent sort of the source bit and the target bit and the source bit, like so. And then there are some technical conditions by which you can say essentially that these things are going to look like string diagrams, and those are called monogamy and acyclicity. And they're kind of the obvious things. You don't really need to think about that too much, but it gets rid of this sort of nasty thing in this picture where we have this kind of backwards loop going to the vertex, and then this sort of disconnected node, which doesn't look very string diagrammy. And then, so what these guys did in string diagram rewrite theory is they proved a sort of representation theorem, which is that if you were to restrict this category of cospans to just these hypergraphs with interfaces that satisfy this sort of thing, then that forms a symmetric nodal category. And furthermore, that is going to be equivalent to some prop, which is generated by the sort of monoidal signature of which you're working. And what that means is you can really draw sort of pictures like this. Weird horizontal line here, but you have an association of the thing that you're actually modeling here, the string diagrams, and this thing, which is just like a fancy graph, which you can easily put in a computer. Okay, so then the next step, once you have like a data structure for your string diagrams, is how you're going to represent your programs as string diagrams. So what we did is we, I think Dan and Fabio worked on this a lot. They wrote like a book about this, but essentially we define like a toy language, which is going to look like the lambda calculus with recursive let bindings. So you have this sort of binding construct here, but otherwise it's just a sort of textual ASCII lambda calculus, and you have sort of imagined operations, which is just going to be syntactic. So a plus operation with arity 2 and like outputs a value, and you can model things like equality and conditionals, ifs, and stuff. And the semantics are going to be sort of string diagrams in traced Cartesian closed categories, because we've got this recursive thing going on. And we also are able to do some thunking, which is where the closeness comes in. So we don't actually have like a compiler for this language, but the point is that it's like a stand-in for an intermediate representation used inside of a compiler, and it corresponds nicely to a string diagram calculus in a purely sort of syntactic way. Nevertheless, you can still write a program and sort of imagine what it might mean. But the main thing that we care about is that you can write this sort of imagined factorial program and then render it out as a string diagram, where now the sort of wires are representing some data flow, and the loops are representing sort of recursion in the data that is flowing through this picture. The box is, so what we're doing is we're binding a variable called factorial, called fact, and that's going to have a thunk inside of it. So that thunk is going to be a sort of higher order function, right? It's an encoding of this in a program as a value. Yeah, so the nodes here, they represent operations, the edges represent data flow, and the nested boxing represents thunking. So if instead I wrote this as an abstract syntax tree textually, it would look like this. And I'm going to make an argument that this is going to be a sort of less elucidating way to encode all of the information here. And by the way, this is the kind of data structure that your optimizing compiler is going to take as input. Yeah. So yes, so some problems of abstract syntax trees are they do not support sort of native sharing or alpha equivalence. So if you have this expression and you represent this by an abstract syntax tree like so, then like I said earlier, you have this variable x appearing in inside the data structure. But if you are able to replace x with a different variable, then you have to do a sort of deep traversal where you're looking at every x and you're replacing it in a consistent way, which is not good. Yeah, so if you have an alpha invariant substitution. And what that means is if you have a compiler optimization which recognizes that you can replace an addition of something with itself by multiplication by 2, it needs to sort of traverse down the whole data structure. And there are some sort of techniques to sort of manage this, which are like De Bruijn indices or normal techniques, but they're not really used in practice. And the idea is that you could use string diagrams instead, because with the string diagram representation, you're just going to pull x out of the diagram, it's going to live here, and you can replace it in constant time. Yes. So another problem with the sort of traditional abstract syntax tree way of representing programs is that they don't have good support for binding and shadowing. So here, if you write this program down as an abstract syntax tree, you have y appearing both sort of a bound position and a use position. And there's nothing in the data structure which distinguishes the two. So as a consequence of this, it's not really clear how you could relate this data on the left and this data on the right. But if you do it in string diagrams, it's sort of fairly clear. Can anybody see what the relationship between these two is, just sort of structurally? Yep, you copy, you just boxed it up, put it through the copy. And so another way to sort of phrase this is a pen. Wow. I guess it's not important. Oh, here it is. These string diagrams are quoting something which is a bit more than just alpha equivalence. It's also some sort of linear substitution bit. So I can write 3 different programs. Find A equals 1 and find B equals 2 and plus AB. And I could write the same thing, but I swap the order of these. And I could also just write plus 1, 2. And these would all have the same string diagram representation on the right. Somehow this captures all of these different programs. And here is what a flavor of like a compiler optimization as string diagram rewriting might look like. This idea that if you are adding something to itself, is the same as multiplying by 2 is captured by that equality of string diagrams. So if we have our term like so, then we can do some graphical reasoning and then get our sort of more optimized term on the right. So this idea of using graph-like structure isn't really super novel in the compiler literature, and many actual compilers do already have data structures inside of them which are used in code programs which are essentially like graphs to begin with. But they're not motivated from a kind of algebraic or string diagrammatic perspective. It's kind of all a bit ad hoc. So the idea is that what we're trying to do is go from the other way, go from the theory and try and maybe come up with a nice graph-based formalism via string diagrams of the kind of stuff that's happening inside of your compiler. Yeah, and here is like a comparison of the sort of different approaches. And string diagrams, we think of them as like an intermediate between just an ad hoc graph representation of a program and this sort of very traditional term tree thing. And another part of this work, which I could give a whole talk on, but I'm not going to today, is how do you draw these things? Because that's a lot of the technical work in this this project was basically about how you do this. So this basically involves taking your hypergraph and then assigning everything to layers, because you need to do that in order to pull out a term in some sort of monoidal category out of it. And then you have to solve this NP-hard problem, which is like minimizing the number of swaps. And then, so the way we actually do that in practice is we generate a massive linear program, which has constraints in it, which encode things like try to center things and try to center things and don't put things too far away unnecessarily in order to get what we call aesthetically pleasing string diagrams. Okay, so I'm going to talk a little bit about LLVM before, LLVM now. Just, I'm curious, can I get a show of hands who's heard of LLVM? Oh, okay, so like almost everyone here. But basically, the anatomy of a modern compiler is you want to separate out all of these different concerns. So you'll have something called a front end of your compiler and a back end of your compiler. And the idea is the people that think about the high-level programming languages and the people that think about the hardware tend to be very different. So the front end is your sort of machine that takes in your high-level programming languages like Swift and Rust and C, and then it turns it into something which is an intermediate data structure which represents your program in the compiler called LLVM-IR. IR stands for intermediate representation. And then LLVM will do a bunch of optimizations on that. And then it'll have different backends, one for like your MacBook, one for Intel x86, that it uses to generate machine code. And this is like where the instruction scheduling and stuff happens. So this is necessitated by two sort of main things. One, you only want to write these compiler optimizations once. And two, you want to solve the sort of NM problem of, I want my programming language that I've just designed, the prototypes, to run on all of the hardware available, even though there's like a billion different instruction sets. And there's going to be more with like all the machine learning and GPU stuff. as well. So yeah, LLVM-IR is, you can think of it as like an idealized assembly language, which is really encoding some sort of graph structure in a textual way. So here is an example C program, which computes the Fibonacci function. And there's a very subtle bug with this program. Can anybody spot it? It's like really hard to read probably, so I'll just move on. But anyway, the LLVM-IR that you get looks like this. This is kind of like an assembly language. And what we could do is we can pass this to our tool to visualize this now as this bunch of string diagrams, which is quite nice because even without this, there isn't a principled way to sort of visualize your programs. And this is useful because the way that optimization passes are developed in compilers is they spend ages looking at compiler output. So there's sort of 3 blocks here that correspond to just this function. It's like the region of code before the loop, the region of the code which is in the loop body, and the region after the loop. This is the loop body, and that turns into this big block here. And what's kind of really neat is that, okay, if you were to, this bit doesn't actually interact with this bit, and if you were to push it along, what that would allow you to do is it would separate this block into sort of 2 logically independent blocks, even though textually the instructions here are interleaved and there's sort of no way to.
Next 4 minutes.
Yeah, sure. Yeah, the bug is that if n is less than or equal to 0, then you return uninitialized here. If the loop never runs, then you don't return anything. And here you can see that you can't see the end, but there's a path from an undefined node to the output of the program, which is kind of a graphical way to see that something's awry. I wanted to do a quick demo. Maybe I'll try to do that. Share screen. I have it loaded up. Oh, no. This is what the tool that we developed looks like. It's got sort of a view of the code on the left and an interactive string diagram visualization on the right. So if I just collapse this left bit, then I can, this is the same program that we were looking before, and look, undefined goes to here, and I can do some sort of basic analysis here. If I ask for this, I can do a sort of interactive exploration of what's going on by reachability in this hypergraph. So yeah, it's kind of marrying theory and applications in that we can actually take output from a compiler and then make nice string diagrams out of it. And I think that basically takes me to time. So I will leave you with some references and be happy to take any questions. Thanks for your attention.
Thank you. Any questions? Javier?
So your tool, you have to the user find the bugs.
Yeah, so it's not an automated analysis tool, it's a program visualization tool. Yeah. Well, it's not really clear what that would mean because we only sort of model programs syntactically, right? So we would need to have some sort of understanding of, like I said that you could see a path from undefined to the end, but to sort of the framework we're working in our program, undefined is just the name of some operation. It would need to have sort of special meaning in order for you to say, oh, this is undesirable, I guess. Yeah, it's probably possible, but it's not something that we looked at yet. But yeah, that would be definitely interesting to do.
Thanks. Another question? Yeah. I expect I can figure out the answer to this, but you gave your example earlier of replacing adding two of the same thing together with multiplying by 2.
Yeah.
And as your example, you showed identifying two subgraphs that are the same and then moving them up, so performing the string diagrammatic manipulation.
Yeah.
Which was someone, for a human looking at a string diagram, that might be feasible, but it does seem a lot harder to do automatically or manually, like searching for two things which are the same in this big graph you end up with, compared with like the difference in efficiency between like adding two identical things together and multiplying them by 2.
I mean, it's kind of a toy example, right? But like the other half of this work that I sort of alluded to when I was telling you about hypergraphs is they worked out the rewrite theory in terms of like kind of graph rewriting, framing these hypergraphs as something that you could that support this sort of efficient subgraph selection and replacement using double push out rewriting machinery.
So you're saying that there is an efficient way?
Yeah, there is an efficient way, and it's algorithmically possible. We haven't done it in our tool, but it's something that would definitely be nice to work towards, I think. It's sort of, we're exploring the beginnings of what it might be like to use string diagrams as like a foundational data structure in a compiler. We just haven't gotten there yet. There's still lots to do.
Okay, I think that's a good point to finish. Let's thank Nick again and all the speakers. And I think Mina and Robin probably deserve a round of applause as well. Want to say something? Rousing?
I don't have anything more, sorry. Thank you all for attending. Have a safe journeys for your respective destinations, and I hope I can see you at another SYCO event. Hopefully not.
So that was a joke. Robin really enjoyed organising this
Yes,
SYCO, and we're always looking for proposals of where we could host future SYCOs. We run 2 or 3 a year normally. If you're interested maybe in thinking about hosting future SYCO, you can be anywhere in the world. We've had SYCOs in Europe and in the US, and there's no particular restriction. Then email someone from the steering committee and to start discussing that. Okay. That's it.
Oh, thank you to them.